Welcome to our data analytics using R full course. In today's world, data is all around us. Every click, purchase, and online interaction creates information waiting to be explored. But raw data by itself doesn't tell a story. It needs to be analyzed, interpreted, and transformed into insights that drive decisions. Now that's where data analytics comes in. In this course, you will learn how to use R, which is one of the most powerful tools for data analysis, to uncover trends, visualize information, and apply techniques like time series analysis to solve real problems. Everything is explained step by step, making it perfect for beginners and those looking to strengthen their data skills. You will dive into R's core features, see how it compares with Python, explore top tools used by data professionals, and even get interview tips to help you stand out in the analytics job market. And by the end of this course, you will have the skills and confidence to analyze real-world data, create meaningful visualizations, and make data-driven decisions, building a solid foundation for an exciting career in data analytics. So let's get started. Also, if you are interested to supercharge your career in data analytics, then the Professional Certificate Program in Data Analytics and Generative AI by Analyst Academy IIT Guwahati is the perfect choice for you. This 11-month live online course offers interactive masterclasses by IIT Guwahati faculty and industry experts combining cutting-edge tools like GenAI, ChatGPT, Python, Tableau, and SQL. You'll get to experience hands-on learning with real-world projects and immerse yourself in the campus environment with a special session at IIT Guwahati, plus earning an executive alumni status from IIT Guwahati and IBM recognized certifications to stand out in the job market. So guys, hurry up and enroll now, and you can find the course link below.
Welcome to Data Analytics with R from Simplilearn. So are you excited to begin with today's session? Yes, you are? Okay, great. I'm excited as well to be a part of this session. What are we going to cover in today's session? We will cover a couple of topics. We will begin with understanding the basics. We will focus on why data analytics and the importance of data analytics. And then, what is data analytics? We will also focus on understanding the life cycle of data analytics. And I'll also try to give you some real-time examples so that we can relate these concepts with the real-time examples or scenarios. And then we will understand the types of analytics and what do they mean. We will also focus on the benefits of using R. For this session, we will be using R Studio tool. Hence, we have to understand why we use R for data analysis. And finally, we will perform some hands-on exercise. In today's session, we will only focus on how to import the data, how to structure the data, and also how to create some beautiful visualizations by using R Studio. All right?
Python and R are top programming languages that are in demand in data science community. Both have their own pros and cons. Therefore, it is vital that you understand the crucial differences between the two programming languages and decide which one is the best fit for you. After watching this video, you will understand which language is better for you in terms of different parameters. Before unwrapping today's topic, I request you to subscribe to our channel and press the bell icon to never miss any updates from Simplilearn. And also get notified every time you get a similar video. Now let us look at what are we covering today. We are covering Introduction to R and Python, Parameters in R and Python, Best Tools and Libraries offered by Python and R, and Conclusion to the topic. Introduction to R and Python. Let me ask few queries regarding Python and R. R language is superficially related to Python, C, C++, Java. Please leave your answer in the comment section below and stay tuned to get the answer. And another question is, which one of the following is a Python file extension? .p, .python, .py, and .pyt. Please leave your answer in the comment section below. Coming to Introduction to Python and R. R is a statistical programming language and environment that integrates statistical computing and graphics. R is powerful and stable software. Python. Python can also be called as a general-purpose programming language for data analysis and scientific computing. Python can be considered as the best player in machine learning. Python is an expressive language with many built-in functions. Both are open source software and platform independent. And they are platform neutral and also compatible with all major operating systems including Unix, Windows and Mac. Next, we will be covering different parameters. We will be covering learning preferability, mathematical fundamentals, speed of both the languages, visualization and graphics, data handling capacity, demand, community and customer support, employment possibility in both the languages. Let us cover it one by one. First one is learning preferability or ease of learning. Python is renowned for its ease of use. Python's notebooks offer excellent tools for sharing and documentation despite the fact that there are currently no GUIs for them. Programmers find R as difficult language as a beginner. This implies that the programmers must devote a significant amount of time to learn and comprehending R coding. Coming to mathematical fundamentals required. Coming to Python, understanding descriptive analysis is very important. In layman's terms, descriptive statistics often refers to the process of explaining using certain representative techniques such as charts, tables, Excel files, etc. Python statistics is a built-in library for descriptive statistics. If your data sets are not too big or if you can't rely on importing other libraries, you can use Python. On the other hand, R requires basic statistics. From basic statistics, what I mean is mean, mode and median are the terms used most frequently in basic statistics. It is referred to as measures of central tendency. Probability statistics plays an important role in handling various types of probability distribution. It includes binomial and normal distribution. Next parameter is speed. Python is an interpreted language with dynamic typing. Python always executes slowly because the code is executed line by line. Compared to MATLAB and Python, R language is significantly slower. R packages are substantially slower than those for other languages. Now that we have covered speed, coming to data visualization and data collection in Python. When selecting data analysis tools, visualization are crucial and Python has some incredible visualization tool. In Python, to large and varied scatter plots using regression lines, we can use ggplot2 and ggplot tools. Compared to raw values, visualized data is easier to comprehend. Therefore, R has many packages that offers sophisticated graphic features. In R, we can use tools like matplotlib, Seaborn, etc. Data handling capability in both Python and R. The new releases in Python have resolved the issue with the Python packages for data analysis. R is useful for analysis because of the abundance of packages, accessibility of the test, and benefit of employing formulas. However, simple data analysis can also be done using the need to install many packages. Crucial part of parameter, that is tools and libraries in Python and R. As a Python developer, one needs to be well versed in the best libraries because Python has a lot of libraries that have many different uses. Libraries like TensorFlow, Scikit-learn, NumPy plays an important role in solving many Python-related problems. Libraries perform a wide variety of tasks in R that are very beneficial for data science operations. Example for that is dplyr, bioconductor, etc. Community and customer support index offered by Python and R. Compared to R, Python has a larger community. For assistance, we can contact www.python.org. For any queries regarding Python and help, you can visit support.realpython.com. For any help and queries, R offers you with RStudio community. R provides assistance through its official website. For queries and community-related issues, we can contact www.r-project.org. Next is job opportunities in Python and R. A recent survey from Indeed.com predicts that at least 55,000 Python jobs in the USA with exponential pay rates are available. Big tech companies like Google, Amazon, Twitter, Facebook requires Python developer to handle massive amount of data. Position provided for a Python developer is software engineer, data analyst, data scientist, and many more. Career in R is an excellent job opportunity for you as a beginner. Big tech companies like Google, Twitter, Facebook are using R. Position provided by companies as a R developer is data scientist, data analyst, data visualization analyst, etc. Moving on, let us wrap up an important topic, which language to be used between R and Python. There is no right or wrong way to study both Python or R. Both are in demand skills that will enable you to complete almost any data analytics work you come across. It ultimately depends on your background, interest, and career objectives that which one is better for you. But compared to R, Python is easy to learn. Let's compare its strengths and weaknesses. It is used to handle large amount of data. Python performs non-statistical functions and it is best suitable for programming. However, Python is better when it comes to coding. Whereas R is used in data visualization graphics, R is a widespread language in the statistical community. It is used to accomplish many mathematical tasks. So before concluding the topic, let me answer the query that I have asked regarding R and Python. Do you guys remember the question? The query was, R language is superficially related to which language? So the answer for the question is C language. Next question was, which one of the following is a Python file extension? It was an easy question. Answer for that question is .py.
So, firstly, let us understand why data analytics. Can somebody here tell me why data analytics and why is it used in organizations? So, let us understand why data analytics and what is the use of data analytics. As we all know that data is growing exponentially year over year. It is collected and it is also available everywhere. Data is no more just available in structured format, but it is also available in semi-structured and unstructured format. I'm sure you would have come across this term called as sentiment analysis pretty often, right? What does that mean? Can we perform that in data analytics? Yes, right? We use some natural language processing models, try to identify what are the good reviews, what are the bad reviews spoken by the customer, correct? So we try to classify the text based on the good, bad, and the neutral. So that is what sentiment analysis is about. So for that, to perform that activity, we have to also do some data analytics. Now that companies have realized the importance of these informations, not just structured but also unstructured data format, the companies have started utilizing these data to take some crucial business decisions, which can boost their business and also which can increase the efficiency of the business. So now that the raw data is accessible to the organizations, it becomes very important that the data is also stored well. I'm sure you all have pretty much heard about data warehouse. In the last few decades, the trend was mostly on the data warehouses, the business intelligence tools. So the data warehouse used to collect this data, pre-process the data, and also filter the data and make it available in a structured format for further analysis. However, now that is not the scenario. A term coined as data lake is available, and many firms are utilizing data lake because it is a central repository which stores the raw data in form of structured and unstructured data. And now let us take a scenario. Let us choose one of the participants here, Mark. So Mark has recently joined an organization as a data analyst, or in essence a data scientist. The business connects with him and says that, Mark, we have a business problem for you and we expect you to provide us a data analytics solution. So Mark sits with the stakeholders and he listens very carefully to the business question. So the business question says that we have a couple of products which are performing really well in the market and we see higher sales. And some of the products are just not catching up in the market and we experience lower sales. Can you help us identify what are the factors driving these higher sales and the lower sales? Now, Mark has to think with the data scientist mindset and be prepared to ask them right questions. Some questions such as, do you have the price of all these products available in the database? And can I also know what is the duration of data availability? And also, Mark can ask some questions such as, do you also have some features of these individual products already captured in your database? So these are some of the interesting questions that makes sense to the business, and the conversation continues, which also means that data is not only information. Data analysis is about unlocking insightful information from this raw data. And hence, data analysis plays an important role in discovering insightful information, asking questions or answering the right questions, and also predicting the future or the unknowns. And to perform all these activities, we use data analytics. So are you all with me so far? Are we on the same page? Yes? Great. Now the question is, what is data analytics? So can somebody tell me what is data analytics? So let us see what is data analytics. We understood why data analytics and the importance of it. But to perform any activities, there has to be a process, right? So data analytics is a process to extract meaningful insights from data. Now let us continue with the scenario of Mark. So Mark now understands the business problem, and he has also started asking some relevant questions to the stakeholders, and he has also got the answers in return. He may start thinking about what could be the suitable solution for this. He may have to perform some exploratory data analysis to unlock some hidden patterns, to identify some correlation between the variables and to also know which are the key variables in the data set. And he may also have to view the market trend, which means he may have to see that how the sales has been performing across the years or across the months. There might be some insightful information there. He may see that the sales has been growing exponentially for some of the products, and some may be volatile, some may have some seasonality pattern or a cyclical pattern, etc. And also he may have to focus on the customer preferences via the customer reviews and do some sentiment analysis. So now let us understand what are those life cycles of data analytics. We will begin with the discovery phase. This is the first phase. Now that Mark has understood the business problem, he will also start focusing on identifying the resources, that is the data resources. Some may be internal data resources that is available within the firm, could be some transactional data, and some external data sources may be via web scraping, identifying and capturing some competitor price on the products. After gathering all of these right data, Mark will focus on data preparation, which is the next phase. Now Mark, either individually or along with the team, will start focusing on the data preparation, which includes data wrangling, which means cleansing the data, imputing the records if there are any missing values, or he may also go ahead by removing those records if they are not required, and also doing some exploratory data analysis, which can include some statistical analysis like looking at the data distributions, understanding the summary of this data distribution at individual variable level, doing some bivariate analysis, and also trying to figure out which are the important variables that might be required for the model building phase. After performing all of these EDA activities, which also include some visualization, Mark will now sit with his team and try to identify the suitable models. The suitable models could be simple statistical techniques, or it can also be some machine learning models. So let's say that Mark and his team has identified some 5 models that can provide the required result. And out of these 5 models, they will filter down and they will prioritize only 3 models. Now there are only 3 models that Mark and his team have finalized. After this, they start focusing on model building activity. Now for model building activity, they have a data set already in place. So this data set will be split into training data set and test data set. It's not only training and test, we can also do some validation in between training and test. But here let's focus on training and test data set. He will separate 75% of the data as training and 25% of the data as test. Now if your question is that why perform this activity of splitting the training data set and test, can't we just go with the one single data set? What happens if you just utilize one single data set? Let us say that you have used the original data set and also executed this data in one of the selected model, and you will also observe the accuracy. Let's say the accuracy returned is about 98%. 98% is a very good accuracy percentage, and you may also be overconfident because of this. That may be a case due to overfitting. Now what will happen when you add some new records into this data set and you rerun it? The executed model may not return you the same accuracy what you had seen. the accuracy might be 72%. Now that's not fair, right? To avoid these overfitting issues, we ensure that some new records are tested separately. So hence we locate 25% of the data to the test data set. And then we predict those records, the unknown records which is located in the test data set. We predict them and then we test the accuracy of training data set and the test data set, and we make a comparison. Now let us say the accuracy result of training is 98% and the test is 97%. In this case, we can say that the model is performing really well. However, while executing the model, there are certain things that has to be considered. For example, inclusion of the parameters, tuning the parameter, which also will execute the optimal results. So this is very important. Now let's say after performing this model building, the time comes to analyze the results. That is the next phase. Now the team will sit and analyze the result, and they will notice that out of the 3 filtered models, only 2 models are returning excellent accuracies. They will sit with the business team and they will also explain them the result and what are the activities that they have performed to obtain this result. Some of the stakeholders may be technically savvy, some of them may be non-technical people. So it has to be very important that you also communicate these results accordingly. Alright, now that you have the results, you will also gauge them based on the business objective, which was developed in phase 1. Looking at the results of the 2 models, now the business might select one of the model and say that, okay, this particular model seems to be returning some right information and it also appears valid to us. Let's go ahead with this one model. So finally, the result and the model needs to be operationalized. And that is where the team will start documenting the business problems, the steps that were taken for executing the models, and they will include all the codes and the findings. And finally, they will implement this model so that the business can view the results and also utilize them for strategic decision making at your firm. So are we good so far with the understanding of the life cycle? Alright, great. Now let us focus on the types of analytics. What are the types of analytics? Can somebody tell me which are the types of analytics you are aware of? Okay, predictive analytics, great. Descriptive analytics, good. Alright, good enough. Now let us focus on this example of Google Maps. So as we look at this particular Google map, we understand that the blue color route is nothing but the route direction from Sacramento to Florin. And also we see a display of the duration estimated as well the distance to travel from Sacramento to Florin. As well we see another route here that is gray colored. This is a substitute route or the connecting route just to avoid the traffic, which is in orange within the blue color route. So the gray colored route as well shows us the estimated duration to travel as well the distance. Now let us understand what is descriptive analytics and why do we focus on this particular map example. As we understand the route map, the estimated duration as well the distance to travel via the blue color route as well the gray color route. This is one way of understanding descriptive analytics, as in what is happening. But there is another way of understanding descriptive analytics, that is by focusing on summarized past data. And this is a descriptive analytics. we see that what had happened in the previous year. Now let us focus on predictive analytics. What is predictive analytics? This type of analytics looks into the historical and present data to make predictions of the future. What does this mean? So Google has already suggested the best route, which is the blue color route, to travel from Sacramento to Florin, and the duration is 18 minutes and distance is 9.7 miles. Let's assume that Google Map has already collected historical data of this particular route, and based on the available data, their model has predicted the best route and also the duration that will be taken to travel from Sacramento to Florin. Now let us focus on prescriptive analytics. Prescriptive analytics describes the solution to a particular problem. What was the problem in this case on the predicted best route? Some predictions on the traffic congestions. And that's when Google Map recommends the substitute routes, correct? Now these substitute routes are also prescribed by Google Map as a recommendation. So prescriptive analytics is nothing but a solution and a recommendation provided for a problem. So in this case, we have the best route and we also have other substitute routes. So let's quickly summarize. Descriptive analytics is about summarizing the past data or to see what is happening, for example, in the Google Maps scenario. Predictive analytics is about what would happen. And prescriptive analytics is about prescribing the solution, the best solution and the recommended solutions. Now let us refer back to Mark's earlier scenario. Mark along with his team identified the best model. They also did some testing and they identified the best results, and they also finalized on one particular model. Based on that particular model, now the results have to be provided in such a way that they are the best results and also the recommendations, correct? So it may not be just one single solution. It may be a solution with couple of other recommendations as well. So that is exactly what happens in the entire process of data analytics. I hope this has been clear so far. Yes? Okay. And now let us focus on benefits of using R. Why do companies extensively use R for data analysis, and why is it chosen? Firstly, R is an open source programming language, which means that there is no license required to work with R. And R does not require you to have a coding experience, which means that a non-technical person in your team can also learn R very easily and start coding or building models in few lines of codes. R can also be used with other programming languages such as Java, C++, and Pythons. And the integration of R with other programming tools or BI tools is very simple and easy. And various statistical models are readily available in R, which also means that there are plenty of inbuilt libraries and packages already available. And reporting the results of an analysis becomes easier by using these inbuilt packages and for creation of these models in just simple few lines code. With this understanding of the benefits of using R, let us quickly hop on to R Studio and start performing the hands-on exercise for data analysis. For this exercise, we will use a dataset named as demographics, which is in a .csv file type. Firstly, let us load the dataset to R Studio, and we will locate this in a variable named as demo. We also refer to this as a data frame. And now you will notice that a variable is created in an environment section, which is in the bottom right hand side of the R Studio window. And this particular variable comprises of 510 observations or records with 8 variables. Let us simply expand this particular data frame and have a quick check on the data structure and understand the data types. This particular data frame includes variables such as age, marital, income, the unit of income is dollar per day, education levels, the car price, car category with several levels, gender, and retired status. Now let us view the top 6 records of this particular data set. For this, let's simply type head of demo. And the result is now visible in the console section. If you're interested to view all the records, then simply type view of demo. And this new window will show you every single record that is being loaded to RStudio. You may also simply apply the filters and the filter section here on individual categorical variables. Now that we have loaded the dataset and also viewed individual records, let us focus on creating subsets of records by applying filters on individual variables or multiple variables. So firstly, let us apply filter on gender. We will only retrieve the records where gender is equal to female, and we will locate these records in a variable named as demo2. As you notice now in the environment section, the second variable is also created, that is demo. And this now is comprising of 250 observations, which means the records are filtered down to only gender female. Next, let us see how to apply a filter on income variable. Let us only retrieve the records where income is greater than 100. Let's view the result. As we see here, all the records include income greater than 100. Now let us modify this query and we will ensure that the retrieved records includes income greater than 100 and also specific variables are returned. Let's say we only want to have the first variable, third variable, and the seventh variable returned as the result. Let's have a quick check. So we only have the first, third, and the seventh variable returned. How about we only exclude the variable 6 to 8? For this, we include a prefix of minus sign. And now let us see what is the result. We have the variables from first to the fifth variable. However, we don't have 6, 7, and 8th variable. I hope it's clear so far. Yes? Alright. Now let us see how can we apply condition by including both the variables, that is gender and income, and then we will filter the record and create a subset of data. Now let's view the result. Income is greater than 100 and the gender is only female. This is one way of creating subsets. However, now let us see how to use the subset command and create the subset. Let's create a subset of records by applying filter on marital status and age. We'll only retrieve records where marital status is equal to married and age is greater than 35. Let's now view the result. So here we have the age greater than 35 and marital status is married. Let's use the same code, and this time we will retrieve selected variables. Let's say variables ranging from 1 to 3. Let's have a quick check. So there are 3 variables. Age is greater than 35 and marital status is married. Now let us see how to structure the data by sorting the data frame in ascending and in descending order. We will apply this order function on the variable income. Firstly, let us see how to order income variable in ascending order. Let's do a quick check. And here we have income in ascending order. Now let's see how to modify the same code and view the records with income in descending order. So we have now the income in descending order. How about include 2 variables and sort the variables accordingly? Firstly, we will sort the records by ordering income and age in ascending order. Let's quickly view the result. We have income in ascending and age as well in ascending. Let's now modify this code. This time we will order income in descending and age in ascending. Let us view the result. So the income is in descending and age is in ascending order. So hope this is clear on how to sort the data frame by ascending and descending order per variable or by using multiple variables. With this, we will focus on learning statistical analysis. How to perform statistical analysis on individual variable or multiple variable. Let's start by understanding the data distribution of variable income so that we identify what is the minimum value of income, what is the maximum, what is the range, what is median, what is the mean, and we will also focus on the quantile distribution, which is also analyzed in a box plot. What is the minimum value in the variable income? It's 9. And what is the maximum? So we have the maximum value. Now let us see what's the range. So the range shows you the result with minimum and the maximum value. How about the difference of maximum and the minimum? Now let us focus on other summaries of data distribution for this variable income. Let's identify what is the mean value of income. The mean is 78. Let's also understand what is the standard deviation. Alright, so the standard deviation is $112. Let us see what is the variance. The variance should be larger than the standard deviation. Now let's say what is the median absolute deviation. As you notice here, the median absolute deviation value is lower than standard deviation. Why do we make this comparison? From this, it is evident that median absolute deviation is robust to outliers and standard deviation is sensitive to outliers and also to the change in the mean value. Now let us understand the quantile distribution. This is the same analysis that is visualized in a box plot, ranging from 0% to 100%, identifying the individual data points. And we can also refer and compare this to the min, the max, and the median values. Let us quickly see what is the median value of income. As you notice here, the median is 45. As well, the 50th percent of quantile is 45, which means 0% is minimum and 100% is the maximum value. Now, if your question is what is 25% and 75%, this is again used for identifying the range of interquartile. The interquartile range is nothing but the difference of 75% minus the 25%. Let's quickly see what is the IQR of income. The IQR of income is 58. Let us do a quick check. 75% of quantile is 86 and 25% of quantile is 28. And the value is 58, which is equal to the IQR result. Now that we have focused on the statistical analysis of the individual variables data distribution, let us focus on the data visualization. In this, we will have a pictorial representation of analysis to identify the outliers, to see what is the minimum and where do we see the data densely populated and how is it scattered, etc. We will begin with creating a histogram. Now, histogram can be used for univariate analysis, which means in this scenario, we will consider income variable and we will see how the count of income ranges gets distributed in a histogram. For this, we will have to install a package called as ggplot2 and also call this library ggplot. Let us install the package. Now let us call the library. Alright, and we are ready now to begin with visualization. For this, we will use the geometric object histogram on the data demo data frame. Let me expand this window so that the code is visible, and also use an aesthetic mapping for variable income. This will be helpful for filling colors or filtrations, etc. And only include 30 bins with individual bin size width of 100, which means there will be 100 incomes in individual bins. Let's quickly look at the distribution of this histogram. As you notice, there are a couple of outliers. The counts of these income range are very limited. However, we see the densely populated income ranges with higher counts between 0 to $200 per day. This is also a way to identify and segment the customers based on their income ranges. Now let us see how to change the color of this histogram and also the border of the histogram. For this, we will include some additional options such as fill with blue color, and the border color is black. Now as you notice here, the executed code provides us the histogram with blue color bars and black color border lines. Now we will focus on creating a facet grid. Facet grid is also an aesthetic mapping object. We will see how to enable the multiple histograms across the marital status and the genders, so that we identify how the income is distributed for individual marital status as well the genders. Let's zoom this view and have a look at it. As you notice here, there are some interesting outliers here in the data distribution. Female unmarried drawing higher income, and male unmarried and married also drawing higher income as compared to the females. Whereas if you notice that the female unmarried is drawing much higher income than the male. This may also be very much related to the age. Now let us see how to create a stacked histogram. When I say a stacked histogram, I mean instead of filling the color, we will fill the gender, so that there is a stack within the histogram. So as you notice here, I have made couple of changes. I have included fill equal to gender within the aesthetic mapping. Now let us look at this histogram. As you see here, the gender is filled in the histogram, hence we have stacked distribution of female and the male. Now let us focus on creating a bar chart with education versus income, where we can identify the education levels and the income ranges for these education levels. As you notice here, we are going to create a visualization where we have the aggregation in form of mean, and the geometric object used here is bar plot. Now let's zoom this view and understand which education level have higher average income. So as we see here, the blue color bar is the post-undergraduate degree, which means this education level draws higher average income as compared to other education levels. Now let's create a histogram where we will see car price and the number of cars for individual category. Let's look at this visualization. This visualization provides us some interesting insight. Just by looking at the distribution of the car prices and the counts of the cars at the car category, economy, and even the luxury. Luxury car category or car price is pretty much distributed, whereas economy car category is dense, which means that we could also look back into the income and age variables and try to figure out further more insights, and then segment the customers for further targeting of these customers. Now what happens if we simply change this bin width to 30? As you observe here, changing the bin width or increasing the bin width will also reduce the number of bins. Now we only have 4 bins here, and the car category is filled. That is what we have enabled within the aesthetic mapping. And we see some more interesting insight. As you look at the standard and the luxury car category, the car prices are pretty much overlapping for the car category luxury and standard. This could be the starting car price of the luxury brands. Now let us create a clustered bar chart. Let's look at this visualization. In this visualization, as you observe, though we have enabled fill equal to gender in the aesthetic mapping, we do not have the view in stacked form, but we have the bars one besides the other. It is also because we have enabled a position called as position equal to dodge in the code. Now, what is the insight that we can draw from this visualization? As you see, postgraduate degree with female gender is drawing higher average income as compared to any other education level. Now let us see how to create a box plot for variable income across the genders. So the box plot can be enabled if there is a bivariate analysis to be performed on a continuous variable and a categorical variable, or multiple categorical variables with a continuous variable. Now let's look at this visualization. What does this say? We have data distribution of income for individual genders, that is for female and the male, and we also notice outliers here. Anything above this whisker is considered to be outliers. It might make more sense if we also include some coloring for these outliers, maybe also enable shape. So now we have colored the outliers and it's colored orange. Let's see if we can also enable the shapes. And now we have here the outlier color as well the shape enabled. Now let us see how to enable a violin plot. What is the utility of violin plot? With a box plot, we understand the analysis and the distribution of the data points is to identify the outliers, to know what is the minimum value, what is the max, what is the median, and what are the outliers. But what is the purpose of a violin plot? Let us have a quick check. As you observe, there is some concentration of data points in the bottom of every car category. However, the concentration is higher for standard car category as compared to economy and the luxury. Now, this is an interesting insight that you wouldn't have come across in box plot. The box plot is a very good representation for identifying outliers. However, violin plot will help you focus on the nuances which is not captured by the box plot. We can also simply combine the box plot and the violin plot together. Simply include this geo object. Let's zoom this. Now you have a representation of box plot and the violin plot, both combined in a single visualization. Interestingly, you notice the outliers as well the concentration in the bottom of this violin plot. So this could be some interesting insights that you draw and focus on these data points and understand what exactly is happening there. Now let's focus on the density plot, that is density estimate of the histograms rather than just viewing the frequencies. Now we see the frequency in the y-axis across the income distributions. How about enabling the probability as true so that we enable the density instead of the frequency? So now we have the density in the y-axis, and in the x-axis we still have the income distribution. This is the way of also adding a line plot, which is a density plot on the histogram. Now, as you observe here, the density plot is not in the same level as the bar. So let us adjust this line. For this, we will include adjust, let's say equal to 3. And now let us see how the visualization appears. Now the density plot is on the same level as the bar. Now let us see how to create a cross table for car category and gender. For this, let us call the library DESCR. Now let us create the visualization, enabling cross table for car category and gender. Let's look at the result in console. As you see here, now we see the counts of the gender for individual car category. The values over here represents that there are 67 females falling within the car category economy and 80 males within the car category economy. And for luxury, we see that the count of female is higher than the male. As well, the proportions. Now, how do you understand what proportions are presented here? We may simply turn off some of the proportions like the t-test, the chi-square, etc. Let us see how to enable that. Now let's look at the result. This looks better. Now that we have the counts, the female counts and the male counts across individual car category, we also see the percentages rather than just looking at the absolute value. So there are 45.6% of female within the car category economy and 54.4% of male within the car category economy. Similarly across rest of the car categories. This kind of cross table or a contingency table is also helpful when you want to analyze the different categorical variables and identify the counts or the proportions. Now let us see how to use a scatter plot of age versus income. Scatter plot is a visualization used for bivariate analysis. When you want to perform some analysis between two continuous variables at a data point level, rather than performing the analysis at an aggregated level, such as sum or mean. And now we have a scatter plot of age versus the income, age in the x-axis and income in the y-axis. Though we do not see any kind of a positive correlation or a negative correlation, but we still see some interesting insights over here. Some of the data points are pretty much scattered and much away from densely populated data points. I hope the learning has been informative and interesting so far. We have covered the concepts of data analytics, as well we have performed some hands-on, doing some statistical analysis and also creating interesting visualization. To learn more and further on data analysis with R, please watch the video above.
Everyone. So welcome to this session where we will learn on time series analysis using R programming language. So this is basically a mini project where we will look at time series data and how we can analyze it, visualize it to basically find some important information or gather insights from the data. Now, when you talk about time series analysis, time series is basically any data set where your values are measured at different points in time. So when you talk about time series data, data is usually uniformly spaced at a specific frequency. For example, hourly weather measurements, you have daily counts of website visits, monthly sales total, and so on. So when you talk about time series, that can also be irregularly spaced and sporadic. For example, timestamp data in computer systems, event log, or history of 9/11 emergency calls. Now, when we work with time series data, for example, here I'm taking an energy data set, we can see how techniques such as time-based indexing, resampling, rolling windows can help us explore variations in electricity demand and renewable energy supply over time. Now, here we will look at some aspects of this data set which I am considering. So this is open power systems data set, and here is the data set I have. We can look at the data set. Now this is in a simple format. It has time. It basically has values for consumption, and then you have data for wind and solar and wind plus solar. So in certain cases you have only the date and the consumption, but then if we scroll down, we will also find data for wind, solar, wind plus solar, and so on. So this is a time series data set which we would want to work on. Sometimes you may also have the data collected which just does not have the time, but it may also have timestamp. That is, it would have, say, hour, minutes, and seconds, and that can also be worked upon. So let's consider this data set and let's work on this project where we will analyze this time series data set. Now here we can work on this time series data. We can basically create some data structures out of it, such as data frames. We can do some time-based indexing. We can visualize the data. We can look at the seasonality in the data, look at some frequencies, and also do some trend detection. Now, when you talk about this data set, it has electricity production and consumption, which is reported as daily totals in gigawatt hours. And here are the columns of the data, which I was just showing you. So you have data, you have consumption, you have wind, you have solar, and wind plus solar. So this is the data we have, and we will basically explore, say, electricity consumption and production in Germany, which has varied over time. So some of the questions which we can answer here is, when is electricity consumption typically highest and lowest? How do wind and solar power production vary with seasons of the year? What are the long-term trends in electricity consumption, solar power, and wind power? How do wind and solar power production compare with electricity consumption, and how has this ratio changed over time? We can also do wrangling or cleaning of this data or pre-processing of data and create a data frame, and then we can visualize this. Now let's see how do we do that. So I will open up my RStudio and let's look at the data set. So here is the data set. Now I'm picking it up from my machine. You can also pick it up from GitHub. So all the data sets or similar data sets can be found in my GitHub repository. And here I can look in the data sets. You will find a lot of different data sets here. There are some time series data sets such as power. I can search for power, or you have basically coal, or you have this OPSD Germany daily data set, and there are many other data sets which you can work on. Now, to get the documentation on this project, you can also look in my GitHub repository, and you can search for repositories, and then basically you can look in data science and R, and here there is a project folder where I've given the documentation, sample data set, and also your time series analysis related document. This is also the code which you can directly import in your RStudio, and you can practice or work on this project. So let's see how does that work. So first thing is, we will create a data frame from this data set. Now here, if you see, I'm using header as true so that it understands the heading of each column. I'm also giving row dot names, and I'm specifying date. So there is this date column in the data set as I showed you earlier. Let's look at it again. So you have date, consumption, wind, solar, wind plus solar. So you can suggest that date should become the index column, which can be useful. So you can do this. Now let's just create this. Let's look at what does this data frame contain. And here, if you see, it shows me some data which has been now as a part of this data frame structure. It starts with consumption, wind, solar, wind plus solar. And if you see, this one is becoming my index column. So I can always do a head and look at part of the data frame using head or tail. So look at the first records. So let's see this. Now that shows me the head data. I can also do a tail and look at the ending values. So if you closely see here, we have wind, solar, wind dot solar, and that basically has NA values. So there are missing values, but let's look at the tail, and that tells me that there is some data available for wind and solar and wind solar. Now we can always look in a tabular format using view, and we can look at the data. So this shows me that there are values in these columns. We see NA values, but if I really scroll down, I can see some values which would be available for wind and solar and wind solar. So I can just use view. Now I can look at the dimensions of this particular object, and that tells me there are 4,384 rows and 4 columns. You can always look at the structure, that is, check the data type of each column, which can be very useful. So if I see here, I don't see the date column because date column was considered as an index, which can be useful. But I also look at my other columns. They are of the num types. So that's the data type for each attribute or each column here. Now we would be interested in looking at this date column. So let's look at the data type of this date column. Now if I try to do this, this will show me that this is null because date as a column does not exist because we created it as an index. So if I look at row names, and then I search for my data, show me the index column or row dot names. It tells me these are the values, that's the date column, which we are seeing here. Now, we can access a specific row by just doing a my data and give the index value or row name value. So let's look at that. And that shows me based on this index, you're looking at the value. You can obviously search for a different date, something like this. You can also pass in a vector and you can give range of values. So that is 0, 1, 2006 to 4 of January. And we can look at this one. So it shows me these are the values. So here actually I'm not giving a range, but I'm just selecting multiple values from row dot names. Now we already know that in R you have a summary function, so you can always do a summary, and that gives you for each column, it gives you minimum, first quartile, median, mean, third quartile, and maximum values. So we are looking at consumption, we are looking at wind, solar, and wind dot solar. Now, this is good, but then if I would want to really visualize the data, access the data, do some analysis, then it would be good to take all the columns, and then we can later decide to change the data type of, say, date column if we want to use it. So earlier I was using date as row dot names or the name of the rows or index, what you call in any other programming language. So here I will just use my data set and I'll say header as true. I'm calling it my data 2. Let's look at the data, and this one shows me 5 columns, wherein my first column is the date, consumption, wind, solar, and so on. Now looking at the structure, so let's look at the data type. So it tells me that if now I'm interested in looking at the date column from my data to data frame, it tells me it is a factor with 4384 levels, and these are the values. So it is not in a date time format, it's a factor. Now what we can do is we can convert this into a date format. How do we do that? So let's have a variable x, and I'm going to use as.date function, and I'm going to pass in my date column. So that's assigned to x. Now let's look at the head of x, and it shows me the values. We will also see what kind of class it is, and we will look at the structure of x. So class already says it is date type, and look at the structure, so it shows me the format. Now we have converted this column or column related value into x. Now how do I basically extract values out of it or make it a part of data frame? So first I will use, so all once it has been converted in date format, I will go for as.numeric, and here I will create a variable called year, and I will just do a format on x, which is basically of date type, and then I'm saying %y, so that will get me the year component out of this. Let's look at the values. That shows me year component. Now similarly we can get the month out of this, and then basically look at the month values. We can get the day out of it, and we can get the day component. Now if I look at my data 2, which we had created earlier, this basically had date, consumption, wind, solar, wind, solar. So what I can do is I can add these extracted columns such as year, month, day to my data frame using a cbind, that is column bind, and I will assign it to my data 2 again. So let's do this. And now if you look at head, it shows me date, so that should be date format, consumption. Now this one might not be date format, but we'll see. You have consumption, wind, solar, and we have extracted the year, month, and day, which can help us for group by. We can do some aggregations, we can do a plotting, and we can do various things by these additional columns. Now let's look at first 3 rows here. So I'll say 1:3 for my data 2, and that shows me some data here. You can always do a head and look at the sample of data. So that basically shows me month, day, your columns, and then you have your date. Now what we can do is we would want to visualize this data. We would want to basically understand the consumption. Now as I said, if we want to visualize the data, say for example, I want this, which is consumption of data over years, and this one is in terms of gigawatts per hour, as we were mentioning here, gigawatt hours. So if I would want to create this visual to basically understand the pattern of the data, how do we do it? So we can create a line plot of full time series of Germany's electricity consumption using the plot method. Now, how do we do that? So here, one of the option is I can straight away use the plot method. I can then say what would be in my x-axis, what would be on my y-axis, what would be the type of graph I would want to plot, what is my name on x-axis, y-axis, and this is the simplest way. So I'm saying my data 2, I'm extracting the year column, and here I'm taking the consumption. So let's create a plot. And here, if you see, we are looking at a plot. We do see some tick times, and we see that the data has been divided with every 2 years. So from 2006 onwards to 2016. But then really this data does not give me a very useful way of looking at the data or understanding it. Might be what I can do is I can use the same way, but I can give, apart from x-axis and y-axis, I can say the limits, that is x limit is 2006 to 2018 and y limit is from 800 to 1700. So we can do this, and let's look at this again. This is a plot, but it really does not help me in visualizing and understanding the data. So what are the better options? I can go for multiple plots in a window. As of now, we are just sticking to one plot in window. So if you would want to have multiple plots, you can always change the value here and make it 2 or 3. That will say how many rows and how many columns. So as of now, we will just keep it as it is, par mf row. Now, if I would want to plot, I can straight away give the column name. So I'm interested in getting the consumption. Now I can just do a plot. I'll say my data 2, and I will choose the second column, which is consumption, which we saw here from our data. So consumption was the second column. So I can just do a plot in a straightaway way without mentioning your x-axis, y-axis, limits, and so on. And if you look at this, this one is giving me a pattern. Now here I am looking at x-axis, y-axis, which is not really named. We do not have a name to this graph, and we are looking at the data. It does show me some kind of pattern, but might be we can make it more meaningful. So I can do it this way, where I say my data second column, let's give axis as year, x-axis, y-axis is consumption. Now that has changed, the x-axis and y-axis. Now I can also give some more details. I can say type should be line. I have the line width. I'm saying color is blue. And let's do this. So this looks more meaningful, might be shows a wavering pattern of consumption over years. I can also give a limit of X, that is 0 to 2018, and that basically shows me the range. Now we can change that, and we can be more specific and saying X limit should be 2006 to 2018. And let's look at this. Now this one, once you have given a proper limit, it shows the line graph, and it shows what was the consumption in 2006 and over a period till 2018. I can then use any of these options are fine, but it depends on what and whom you are presenting the data or what kind of analysis you're doing. So I can do a plot. I can choose column second, X lab, which is x-axis, y-axis, type is line, width, giving a X limit, Y limit, and then I'm giving a title to this, which is consumption graph. And then basically you're looking at the line graph. Now, those are the options which you can do. Either you could be very specific, or you could just give your column which you want to plot, or obviously make it more meaningful by giving all the details. Now, what we can do is, if we would want to look at this data and understand it better, rather than just looking at a simple line, I can take the log values. So here I'm saying log of my data to second column. So I'm taking log values of consumption and I'm taking the difference of logs. So I can say difference, and then you can basically increase or decrease this by multiplying it by some number. So rest remains the same. I'm changing the color, and let's look at this plot, and you see this basically is giving me a better pattern, which makes meaning. Here we see the log values. So this is, you are using a simple plot function. In R, you can also use ggplot. Now for that, we can install the ggplot package. It's already there in my machine, so I'll say no. I will access this by using the library ggplot2, and now I can use ggplot to plot. So the way you specify here, you can say my data2, that's the data frame. I'm saying type as O, and when I'm saying line, I am basically going to use x-axis, which is year, y is consumption. And let's look at this plot. So again, we are back to the one which we were doing earlier. Really does not make any sense. It gives us some data, but then really does not give me enough information. I can, in my aesthetics, I can say X as year, Y as consumption. I can do a grouping, and then I can give line and plot. So again, we have some information, but really does not help me, right? Now let's look at other example. So I'm just doing the same thing here, and I'm looking at line type being dashed. I'm using the ggplots other methods such as geom_line and geom_point to give me more information. And if I look at the plot, it does give me data. It tells me what are the different values. It gives me some kind of pattern, but I would still prefer the way we were doing with plot. Now we can change the color and obviously add details to it. So what we see is when you use the plot method, which I did earlier, it was choosing pretty good tick locations, that is every 2 years, and labels the years for the x-axis, which was helpful, right? But with these data points, which we were seeing here, or say, for example, this one, or say this one, or say this one, we are looking at some data, but then that really is quite crowded and it is hard to read. You can look at the values, but then it really does not give you enough information. So we can go for plot method, but then we will see how we can consider different data. Now, if I would want to plot the solar and wind time series, so let's see how do we do that. So wind column is what I'm interested in. So first thing is, it was always good to find out the minimum and the maximum values in every column. So I'm saying minimum. I'm saying let's put in here my data 2, and then let's look at the values. So we are looking at the columns. We know consumption is the second column, wind is the third column, and you have solar as the fourth, and this one is the fifth. So let's say, let's find out the minimum of each of these columns which we would want to plot. So let's say minimum of data third column. And here I'm also saying remove the NA values because we do not want to consider the NA values. So let's look at the minimum. That shows me 5.7757. What is the maximum value? It is 826. So that also helps me in giving a limit. If I want to plot wind on y-axis, I can give a y limit from 5 to 850. Consumption wise, let's find out the minimum from second column and maximum. And similarly for solar, find the minimum and maximum, and wind plus solar, minimum and maximum. So this will be helpful when you would want to plot multiple graphs or give some limits. So that's fine. Now for multiple plots, as I said, instead of having one plot, let's plot consumption and wind and solar and try to see a pattern. So I can say par function, and I will say 3 rows and 1 column. So now when I start plotting, you will see you will have multiple plots in one single window. So let's see how we do it. So here, let's look at plot 1. So this one is consumption as we did earlier. And let's look at the data. So that gives me some data. You can always do a zoom and you can look at the data. you can basically expand this graph, or you can reduce this graph to see what kind of pattern we have in consumption. Similarly, we can basically choose date being x-axis, my consumption being y-axis, right? So this is being more specific, because here we have a range, but it really does not give me enough information. So I will basically give x-axis, y-axis, I will give the name, that is daily totals, and then I will basically give consumption, color, and y limit based on my minimum and maximum limits. So let's do this, and now we can look at the data here. So let's see, this data makes a little more meaning because we are looking at the dates. And let me do a zoom. So it shows me all the dates, it shows me the data points, it shows me how the data pattern is changing for consumption. Now this is for consumption. So what we can do is we can also extract specific data. So if you see here, I have done some testing where I am saying, okay, I would want to get a date specifically. I would want to extract some value. So we are looking at the date column, but if you remember, we did not change the data type. We just changed the data type of date column. We extracted year, month out of it. It would be good if we can convert a column into date time format and put that in our data frame. Now, let's look at the plot 2. This is mainly for your column, which should be consumption and wind and solar. So here I see it is solar data, and I can plot this one to see how it looks like. And that tells me from 2006 onwards, we have some pattern. I can be more specific where I say I would be giving date and then the column for solar, x-axis, y-axis, what is the type, what is the y limit, and what is the color. It is always good to specify your x and y axis, give a name, rather than let it automatically pick up. Now this makes more meaning because it shows me some dates. Similarly, we can do for wind. So either you do it just by giving the column, or you give your x and y axis. So let's look at this one, and this shows me the data. So we can choose plot 3, this one, we can choose plot 2, we can choose plot 1, and we can put all that data in one graph. So that's when you are putting in multi plots in one particular graph. You can always do a zoom, you can always look at the data, right? And this is usually useful to look at the pattern, what kind of pattern we see, what data we have, and so on. Now, moving forward, so we have seen how you are creating these plots all in one window. Let me reset this back to one plot per window, and let's basically plot time series in a single year. So what we have seen is that when you look at the plot method, it was quite crowded. Then we looked at solar and wind, and if you compare that, you will see your consumption pattern, your solar pattern, your wind pattern, and basically we can see from this particular data some kind of pattern. So electricity consumption is highest in the winter, where we will see what is the consumption. Is it highest in winter or is it in summer? We can see that by breaking a year further into months, we can see that. But we see a pattern which goes for every year or every 2 years being highest at a particular point of time, and then it drops down. So electricity consumption is highest in winter, and that might be due to electrical heating and increased lighting usage, and lowest in summer. Now, when you look at electricity consumption, appears to split into two clusters. We can always look at the consumption, one with oscillation centered roundly around 1400 gigawatts. So you can always look at 1400 gigawatts and you see all the values here which are in that particular consumption. Another with fewer and more scattered data points, centrally roughed around 1150. So if you really expand this, you can see you will have a lot of data points at this point. Now, We might guess that these clusters correspond with weekdays and weekends, which we can see if you break that data into yearly, monthly, weekly, and so on. Now, if you look at solar production, that is highest in summer when sunlight is most abundant and lowest in winter. So obviously when you're making or gathering some insights, when you're looking at the data, you are also using your domain knowledge, your business knowledge, your knowledge of business to understand how this goes. If you look at wind power production, that's again highest in winters and drops down in summer. So due to stronger winds and more frequent storms, and lowest in summer. So there is some kind of increasing trend in wind power production over years, which we can see here over the years. And all the time series data what we are looking at is referring or showing us some kind of seasonality. That is, we are looking at seasonality in which a pattern is repeating again and again at regular times, at regular intervals. So if you look at consumption, solar, and wind time series, that oscillates between high and low values on a yearly time scale, which we can break down and see. I'll show you that. It corresponds with the seasonal changes in weather over the year. So seasonality does not have to correspond with meteorological reasons. For example, if you look at retail sales data, that will show you yearly seasonality with increased sales in particular months. So seasonality, when we say, can occur on other time scales. So the plots what we are seeing here, they are fine, but if you look at those plots, they might show some kind of weekly seasonality also. So in your consumption corresponding to weekdays and weekends. So let's plot for one single year. Now, how do I do that? So first is I will look at my data 2. That shows me the structure. It shows me date, which is factor, other columns, which are all numerics. Now, like we did earlier, I'll repeat this step where I'm going to convert the date column into date type, look at head of it, look at class of it, look at the structure of it, right? And then what I want to do is I want to add this to my data frame. So I will create a variable called mod data, and this one will have as data, and I'm formatting the value of X, which is date time, into month, day, and year. So let's do that. And now you look at the mod data, which I created, like modified data. So this is the format I have. It is in date type, if you carefully see here. And then I can look at the head of it. So it says me mod data. Now what we did here is when I said my data 3. So my data 3, we did a cbind and I did a mod data, which is going to add this column to my other columns of my data 2. So my new data frame is my data 3. Let's look at the structure of it, and you see there is this date column. I can delete it, I can remove it, I can let it be, right? So that depends on our choice. Might be we want to, once our analysis is done, we want to remove the mod data, right? So we can keep both of them. Now let's basically extract data for a particular year. Now how do you do that? So this is some wrangling. So I will say my data 4, let's call it my data 4, and I will use subset function. So subset will work on my data 3, that's the data. And what I'll do is I will do a subset. How is the subset found? So I'll say take the mod data column, the value should be greater than or equal to 2017 and should be less than 2017 December 31st. So I'm getting data for 1 year and I'm storing it as my data 4. Let's get the head of it, and you see we are specifically looking at 2017 related data. Now let's do a plotting of this where I will only create a plot for 1 year. So I'm saying my data 4, that's my new data what we got. So here I am going to take the first column, which is mod data. I'm going to take the third column, which is consumption. So I'm looking at the date format for 1 year, consumption values for it, and then rest of the things as we have done earlier. Let's look at the plot. And this makes more meaning, right? So when you look at this plot, it tells me Jan to Jan. It shows me some kind of pattern where I have divided the year into months, right? And it is broken down into, say, 2 months, so Jan and March and May and July and so on. But we still see a pattern, and that gives me good understanding of pattern where I've broken it down into months. So this is where you have taken time series in a single year to investigate further, and this is what we see, right? Now we can clearly see there are some weekly oscillations. What one more interesting feature is that at this level of granularity, that is when you're looking at yearly data, there is a drastic decrease in electricity consumption in early January and late December during the holidays, or probably we can assume that this is holidays. Now I can zoom in further and look at just Jan and Feb data. Let's see how we do that, and let's see how we work by zooming in the data further. So to zoom in the data further, let's see how we do it. Now here we have this my data 4, which is basically having a subset, right? So let's work on this one. So I will say my data 4, which earlier I was taking data 3, I was doing a subset and I was giving the date, but this time I will make it more narrower. So I'll say my data 4, I will say subset from my data 3, and I will choose mod data column, which we have modified with the date format. I will choose the starting date as 1701, that is Jan, and then let's go till Feb and let's create this. Now let's look at the head of this. So it shows me we have the data which is Jan, and then you can basically look at more on this. Now again, as I said earlier, let's find out the minimum of this from the first column. So that is basically your mod data. So let's look into this one, and that basically will give me minimum and maximum. Let's look at the values. So this one tells me Jan 17, January 1, and maximum is your Feb 28th, second month 2017. So we are actually looking at 2 months data here. Let's look at the Y minimum. So this is, I will look at column 3. Now what is column 3? Consumption. So let's look at the minimum value for consumption, maximum value of consumption. Let's look at the values which can be given as our limits. Now this is the minimum and maximum. Now let's do a plotting for this data which has been narrowed down for consumption based on my data. So I'm saying my first column, which is mod data, and then third column, which is consumption. I'm giving some naming convention for, namings for your x-axis, y-axis, what is my consumption, or what is my title here, what is the color, and then you see I'm using X limit to give the minimum and maximum limit and Y limit. So let's look at this data. And if you look at this data, it is specifically for 2 months. And again, I can look at the pattern here. What I can also do is I can add some grid here. So I can basically look at this data and make more meaning out of it. So it is bi-weekly data, you can see. Now I can add a line here using ab line, and then I can basically choose what lines I would want to add horizontally. So that basically allows me to dissect the data and look at data in a more meaningful way. I can also add vertical lines. So vertical lines is, I'm saying sequence will be minimum, maximum, and I'm saying an interval of 7. So let's do this, and this basically has added some lines every week, and you can see at the end of week it is dropping, and then it is starting again. It peaks somewhere in the mid of the week, and again it drops down. So this is, you're looking at your consumption data, right? Now what we can also do is we can create some box plots. So when we looked at zooming in data for Jan and Feb, you can add some data points like this. So consumption is highest on the weekdays, as I showed you here, and lowest on the weekends. So this is what we are seeing when we are breaking the data or zooming it further for a couple of months. So we have vertical grid lines, and we have nicely formatted tick labels, that is Jan 1st, Jan 15th, Feb 1st, and so on. So we can easily tell which days are weekdays and weekends with use of these grid lines and basically breaking it down. So there are many other ways to actually visualize your time series data depending on what patterns you're trying to explore. You can use scatter plots, you can use heat maps, you can use histograms, and so on. Now, moving further, we would want to explore the seasonality, right? So when you further explore the seasonality of our data, we can use box plots basically to group the data by different time periods and display the distribution for each group. Now, how do we do that? Let's come here and let's see how box plot works. So I can just do a simple box plot, and I can choose my consumption column, and that gives me just the consumption data, but this really does not give me any meaning. I can look at solar data, I can look at the wind data, and we can also see some outliers here. So we can create box plots, but if we would want to do a box plot, what is box plot? It is basically a visual display of your 5-number summary. That is, you want to look at your mean, median, you want to look at your 25th percentile, 50 percentile, or 75th percentile. So we can use a quantile function, use the consumption column, and then you basically give a vector which shows you 5-number summary. So that's your quantile. And then let's do a box plot. So if you are looking at quantile, it tells me what is the minimum, what is 25th percentile, 50, 75th, and 100. That's from my consumption column. So let's create a box plot for consumption. Let's give it a name as consumption. Let's give y-axis as consumption and a limit for y-axis. Now that's my consumption graph. So I can look at yearly data. Now that will make more meaning rather than just looking at the complete consumption data. So how do we do it yearly? So we will say consumption, and then I will say the year column. So it is consumption, but grouped based on year. So here I can give x-axis, y-axis, and I can give y limit. So let's create this, and this makes more meaning. We can give some coloring scheme here, but now I'm looking at 2006, 2007, 8, 9, and so on. And we can look at the data, what is the range, right? It gives me 5 percentile, or sorry, 5-number summary of the data per year, and it basically allows me to look at the seasonality of this. Similarly, we can create box plot by just giving consumption, yearly grouped, and here I'm giving the title as consumption, y-axis, x-axis, and y limit, wherein I can also use las. So this is one more feature which you can do, and that basically will give me the tick points. If you compare this one to the previous graph, so when I created this previous graph, I had 2006, 2008, and I had from 600 to 1800. And if I go for the next one, I am basically seeing more useful information. Now let's look at monthly data. So I would want to group it based on months, and let's create that. So this gives me the monthly data where I'm looking at months, and I could select a particular year, or I can just do a grouping based on months. So I can have multiple plots to see a difference here. So let's do this. Now let's create a box plot for consumption, which is monthly data, and let's give it a color. Let's look at the wind data, which is again grouped monthly, and let's look at the solar data, which is grouped monthly. Now, if I zoom in, it basically gives me the seasonality of the data for your wind, for your consumption, for your solar. So what we are doing is we are creating these box plots which are giving us values. Now what I can also do is I could look at the day wise also. But before we look into this, how do I infer some information from these box plots which are being created? So this is what we have done, where we are looking at the data for month, and these box plots give me year seasonality, which we were seeing in earlier plots, but give some additional insights. So if I look at the data here, it tells me the electricity consumption is generally higher in winter. Now this is based on months, so we can see consumption is higher in winters and lower in summer. So we can obviously look at our plot, we can see where it is lower, where it is higher, and then we can look at the median and lower two quartiles are lower in December and January compared to November and February. So that is, you look at the quartiles and you will see that the median and lower two quartiles are lower in December and January. Here Jan and December, so you can look at from my plot. Now this is giving you some idea on seasonality. Now that might be due to business being closed over holidays. Now this one we were also seeing when we looked at time series for 2017 only, and box plot basically confirms that there is this consistent pattern throughout the years. Now when you look at your solar and wind power production, both will give you a year seasonality, what we are seeing here. And if basically I look at the data, so it depends on what parameters you are choosing, but if you look at solar, it will reflect the effect of occasional extreme wind speeds associated with storms and other transient. And since we are grouping it based on months, we can see this pattern is quite evident every year. Now, what we can do is we can group the data day wise. So here, let me again reset this to one plot per graph. Now I'll say box plot, I'll say consumption, which is grouped based on day. Now we know that there is a day column, and let's give a while limit and let's look at the data. So this is where I'm grouping the data day wise. So you look at 31 days and you look at the box plot. So this is where you are plotting it on a daily basis. So you can look at the data, you can break it down to a particular week. So here I have given day and I have chosen all the 31 days, but I can break it down to a week and I can look at the data. So if we look at the data per week or per day, we can basically infer that electricity consumption, where I'm doing a consumption group by day, is higher on weekdays than on weekends. So time series with strong seasonality can often be represented with models that can decompose signal into seasonality and long trend. Now this is an easy way. Now how do we look at the frequency of the data? That could be interesting to see. So let me look at, say, the yearly data which we were seeing here. Now let's go further, and here we have looked at data. So what we will do is we look at the frequency. Now when you look at the frequency, when you talk about frequency in your data, so we have the modified date column which gives me a frequency, and if we really look into the data, that will tell me that the data is on a daily basis. So for that, let's look at my data 3 again, which gives me data, and you can just see all the data or dates are in sequence. So your 22, 23, 24, 25, 26, and so on. I can access a dplyr package that is basically allowing me to work in a better way. Now I can look at the summary of this, and for all my columns, I'm seeing what is the minimum 5-number summary, date, and consumption. So date does not show me anything because this is not in a date format, it is just a factor, but other things have the 5-number summary. So we are looking at wind plus solar, we are looking at year and month and day and all these columns. Now what we will do is we will want to find out the sum of each column, how many entries does it have, and we will say the value should, NA value should not be considered. So let's look at this one. So it tells me for my particular columns. So let me run this again, and that shows me for each column how many values you have, and these counts do not include the NA values. Now similarly, I can find out specifically for consumption. I can find out, is there any NA value? So I'm saying is.NA, and let's find out if there is any NA value or missing value in consumption. It says 0. Okay, that's good. If you look in wind, it tells me there are 1,463 entries which are NA. Similarly, solar, similarly, wind dot solar or wind plus solar. So it gives me a count of NA values, that is missing values, and also values which are not missing. So to understand frequency, what we can do is we can find out the minimum on the date, that is the first column, and I'm saying RM na.rm is true, that is get rid of NA values and find out the minimum. And let's look at the minimum value. This is the minimum from my modified date. Now, if I would want to get the frequency, I can basically use sequence function. So I can say from X minimum, that is the minimum value, I want to look at the frequency, that is day wise. And let's just look at 5 entries and see if there is a day by day frequency. So let's look at the value of this, and obviously it tells me there is day wise frequency. So that allows me to look at the frequency, look at the type of it. It is an integer, class is a date. So similarly, we can say from X minimum, we can basically look at the frequency month wise, and I can again look at 5 records. So that shows me monthly data, right? So I can extract the data for frequency, similarly yearly data, and that's also very useful. Now, we can select data which has NA values for wind. So how do I do it? I would want to find out the wind column, and I want to find out where the values are NA. So I will create a variable, and here I will say my data 3, and then I give a conditional where I say is NA in the column. So let's do this. Now once I've done this, I have said that my selected wind data from my data 3, where we said NA values, and I will give the names to this. So names should be in my data 3. I'm interested in mod data, consumption, wind, and solar. So these are the 4 columns I'm interested in. Let's look at first 10 records here, or first 10 rows. So that tells me these are the values where wind has NA or missing values. I can always do a view, and that gives me the complete data. So it basically shows me 1,463 entries, and here it shows me all NA values. So you can look at all the way to the end, and it shows me wind has NA. Solar does have some value here in the last row, but then also if you see, the numbers have a difference. So you have 1461 and then you have 2174. So there is a difference. So there is some data in between where wind has some values. So we have found out NA values. Now what we will do is we will select data which does not have NA values. So I will call it cell selected wind 2. I'll again use my data 3. I will say which, but now I'm saying not NA from this column, and I will select the data for the columns. So I'm interested in looking at 10 records, and this shows me not NA values, so no more missing values. So if I really look at this data as I saw earlier, which has NA, and if I look at these values which are not NA for the wind column, so looking at these two results, we will know that in year 2011, wind column has some missing values. So let's focus on year 2011. So how do I do that? Let's call it a different variable. I'll say my data 3. I will say here, when I say which, where we were saying NA, here I will say the year should have a value of 2011, and I want all these columns. Let's look at the data here, and this is showing me 2011, but we are not seeing all the values. So there are some values, but then there are some missing values also for 2011 based on whatever analysis we have done. So let's look at the class of this. It is basically a data frame, do a view, And this one will help me in finding out where are the NA values. So if you just scroll down, looking at all the data, let's search if wind column has a NA or a missing value, and I will see if there is any missing value, in which column or which row it is for the wind column. So we have all the values which are existing. I could select and search for one specific value, and I'll show you how we can do that. So here, let's scroll all the way down. So it's like you're exploring your data and seeing, is wind column having NA or missing value for a particular row. And let's scroll here, and here you see there is a missing value for one particular row. So 13th December 2011 has wind value, 15th December has wind value, but your 14th December does not have, right? Similarly, we can search. So there was only one entry which was missing. Now that could be for some reason, might be it was not calculated, might be it was not tabulated. So we have a missing value, and that can affect my plotting, that can affect my analysis. So let's look at the number of rows in this, which will tell me how many rows we have for 2011. So it tells me 365. So that is basically the number of days in a year. Now we will find out if there were NA values. So we earlier checked total number of NA values per column. That is in your row number 265 to 269. We can see here 265 to 269. So this is where we were seeing, are there any NA values, right? So let's go back here, and we want to find out the number of NA values for a particular year. How do I do it? So I can just do a sum. I will say is NA. Now I'm interested in my data 3 wind column, and I'm saying my year has to be 2011, but I'm finding out the NA values. So let's do this, and it tells me 1, and that's right. That's what we saw when we did a view. Let's see how many non-NA values you have, and that is 364. So that basically satisfies my logic. So it's 364 plus 1 missing, so there are 365. Let's look at the structure of this. It tells me you have modified date and date format, you have consumption, wind, and solar. Now let's create a variable, selected wind 4. I will say wind 3, that is which was having all my NA and non-NA values for 2011. I will say let's find out the NA value, because I'm interested in finding out that particular row. So I'm saying find out where the value is NA, and I want all the columns. Let's look at this one, and this is my specific row which has a NA value. Now we know that data follows a day-wise frequency, which we have clearly seen. Now let's select data which has NA and non-NA values. So let's call it test 1. I will use wind 3, which has NA and non-NA values. But now I will say I want the modified date, which should be greater than 12/12/2001. Now remember, we had, when we were doing a view, we saw that one particular day, or what we see here, 14th of December, there is no date. So I will select a subset of data which includes this NA and non-NA. That is, might be I can take 13th of December and 15th of December. So let's start from 12/12. So the date should be greater than 12/12, that means 13th, and it should be less than 16, so that is 15th, and the columns, right? So now we have some data. Let's look at this. So I've selected a subset of data. I could have done this using subset also. So I have NA and non-NA values. Now, why are we doing this? So sometimes you might have some data for a particular column, and you may want to find out if there are any missing values. Might be you want to fill them up or replace them with something. So that is usually useful when you are doing a trend detection. So say, for example, you have data for every month, and might be in one of the months you have missed, or might be you have data for every year collected monthly, and then in one of the years for a couple of months you don't have the data. Like I can say 2016, I have data for all 12 months, 2017, all 12 months, 2018, might be I don't have data for March and June, 2019, I don't have data for same months. So I can forward fill or backward fill them using the previous year's same month data. So we can do that. So here I have test data where I've extracted a subset of data. I can look at the class of this. It is a data frame. Structure of this, it has the columns. Now let's use the library and function and use the tidy R package. And what we will do is we will fill it up. So I will use test one. I will fill the wind column, which has a missing value. Now, once you do this, if you notice, it has done a forward fill. So it has taken the previous value and it has just filled up that. So you can fill up the data using different directions, such as up and down, left and right, and so on. So we can take care of missing values in our frequency data, which allows us to basically analyze the data in a better way. Now, here we will want to also look at some more data. So this is to deal with frequencies of fill column, wherein you can take care of missing values forward filled. So filling values can be done in different directions, as I said, and you may want to first convert your time series to specified frequency if your data does not have a frequency, but we had. Now, if you do not have a frequency, might be you can convert it into a frequency such as weekly, daily, monthly, as I showed you, and then basically you can do a forward fill for the values. So for example, if I have my data, I can break it down into weekly and then look at the values, and if there are any values missing for weekly data, I can use a forward fill. So that can take care of my frequency data. Then let's look at the trends of the data, which is the last part of this project. So basically, let's look at the trend. So when you say trend, what does that mean? So in time series data, you always have some kind of trend. So that will exhibit some slow, gradual variability in addition to higher frequency variability, such as seasonality and noise. Now, to visualize these trends, what we do is we use what we call as rolling means. So we know how our data is spread over year or month or day. But how about looking at a rolling average and see what is the difference? So a rolling mean will tend to smooth a time series by averaging out the variations and frequencies. So this can be higher than the window size. So there is something called as windowing, where you can choose a set of time frame. You can also average out any seasonality on a time scale equal to window size. So this will allow you to look at lower frequency variation in the data. So when we are looking at electricity consumption time series, we already saw there is a weekly pattern, there is a yearly seasonality, which we saw using box plots. So we can also look at the rolling means of the time scales. How do we do that? So for this, you can use some package like Zoo, and then you can basically use a rolling mean using the Zoo package, and you can say what is the frequency with which you want to calculate the rolling mean. Now, how do we do this? Let's look at this data. So here I'm going to look at my data 3, which we have been using so far. Now let's call it a 3-day test. You can give it any name. I'm going to use my data 3. I'm using the pipe in function. Now I will use dplyr and I will arrange the data descending in year. Now you can always break it down step by step and you can see the result of this. So I'm going to arrange this data in descending order of year. So obviously my last one, 2017 or 2018, will be on the top. You want to group the data by year. So it depends on how many years we have, we'll see. So you can group the data by year. Now this data is then used to basically mutate. So mutate function is going to allow me to use this rolling mean. So I'll call it as says 03 day. So I'm going to calculate a rolling mean every 3 days for my consumption column, and basically let's ungroup this. So let's see how this works. Sorry. Yeah, let's look at this. And here, when I'm doing a 3-day test, let's look at the result of this and then I'll explain this. So if you see here, we have the test 3-day column. Now this has the rolling average. Now what does that mean? So first value here, what we see is 1367 is the average consumption in 2017 from the first date with a data point on either side of it. That is, you can look at this date, so 1130, then you look at, you're looking at the value 1367 here, so you look at 1130, 1441, 1530. If I take a mean of these, so for example, if I would just do this part, and that is giving me mean, okay, because I have a comment, so let's basically add anything as comment, and then let's do this. So it says me 1367. That's what we are seeing here, right? So you're getting a rolling average every 3 days. Similarly, if you want every 5 days, it takes the 5 values and it gets the mid value, right? So you can always find out the mean, rolling mean for a particular frequency. Now, let's do that for 7 days, that is weekly data, and yearly data, that is 365 days. So how do I do it? Same logic, my data test. Now I'm using my data 3, I'm arranging it in a descending order, I'm grouping by year. So when you do a group by year, so earlier when we did a grouping by, and when we looked at the data, it was telling me how many rows we had, right? So let's do a grouping by year, and let's say test 07. So that's a rolling average every 7 days, and I'm also saying take care of the NA values. Similarly, I'm getting rolling average every 365 days. Might be you can do quarterly, might be you can do half yearly. And let's do this. So let's create this, my data test, and let's look at the result of this. So I will use my data test. I will say arrange based on modified date. Now we know there is a column called modified date. I want to just look at 2017 data. So I'm doing a filter, right? And then I will choose what are the columns I'm interested in. So I will look at the 7 and 365 day. And let's look at, say, first 7 records. So let's do this. And that basically gives me the consumption value, modified date, year, and my rolling 7-day average or the 7-day mean, which is for first 7 days. And then 365, you will not see the data here, but if I do a view on this, I can basically see the values. So you can always select a particular column to see the values. These are the values for every 7-day rolling average. This is for 365 days, every 365 days. So you see all the values are missing, but every 365 entry, you will have basically some data. Now, let's do a plotting of this and basically visualize this data which we are seeing rolling average. So let me first do a plotting, one plot per graph, and let's do a plotting. I will take consumption data, x-axis, y-axis, color, and give a title to this. So let's create this, and that's my consumption data, which is spread over a period of time, and that's fair enough. But now let's add some more plot to this. So I will add the 7-day rolling average to this. So for second plot to be added in the same one, in R you can use points. So I will say points. I will choose 7 data column, type is line, width, x limit, y limit, and color. So let's do this, and that's my pattern 7-day rolling average, which basically gives me some kind of trend. Similarly, I can add one more here, and this time I will choose the 365 day and look at the pattern lines. So now you see some dots here. Well, you could do it in a different way. So I can just add legend to this, and I can say legend will be where in x-axis and y-axis. So I'm saying it will be 2500 and y is 1800. So my legend will come in somewhere here. I'm saying my legend will have consumption, test, and this one I can give some names. I can give what is the color. I can say what kind of legend, it explains what is for each color, and then basically a vector. So let's add a legend to this, and I've added a legend. Now you can do a zoom and look at the data, and here I see that my x-axis is fine, but y-axis is going a little out of my plotting area. So I can actually change that. So here I have 1800. How about making it 1600? And let's look at this one. So we can basically go for this one and start again here, plot and points and line, and then add a legend, right? And you can basically place your legend anywhere in the plot. So this basically is giving me the trend, what I'm looking at, my rolling average. So similarly, you can look at the trend for wind and solar data. So what we are seeing here is, when you look at trend, this is one more way of looking at it. You can always create plots in different ways. So 7-day rolling mean has smoothed out all weekly seasonality, which we were seeing here in my graph, where you look at every 7-day, preserving the yearly seasonality. So 7-day will tell that electricity consumption is typically higher in winter and lower in summer. So better is you break it down yearly. So here, if you look at every year, you can see when is winter, when is summer, what is the seasonality, what your trend, what you're seeing here, and if there is a decrease or increase for a few weeks every winter. So similarly, if you look at 365, now as I said, rolling average basically reduces the variation. So if I look at 365 rolling mean, we can see long-term trend in electricity consumption is pretty flat. Now that's what we are seeing. It's kind of pretty flat. There is not much variation over years if you really join these dots. So we can basically see some highs and lows, and that gives me a trend. Now this is how you can do a trend detection, and similarly we can do plotting for wind and solar. So this is a small project which I demonstrated using R. Now all this code which you have here in the form of a project.r file, you can find here in my GitHub page. This is the document which explains some things. Feel free to download this and you can add details to it. This is the sample data set, which you can also find in my repository in the datasets folder. So continue learning and continue practicing R.
This is the second part of a two-part series about time series data. In the first video, we saw what exactly time series data is all about, and in this video, we are going to implement it in R. Before we do that, let's do a quick recap of what we did in part 1 of this video, and we will then move into the implementation. So we talked about what is time series. We did an introduction to time series in part 1, and we saw that time series is a sequence of data that is recorded at regular intervals. Could be daily, monthly, weekly, whatever. And needless to say, the data is time dependent. And then we have some historical data. Based on this historical data, we try to predict or forecast some future values. And we also saw that time series data has these 4 components. There is a trend, then there is seasonality, cyclicity, and randomness or irregularity. And we also talked about stationarity of time series data, because before we do any time series analysis, we need to make the data stationary, and the 3 components that are responsible for stationarity are mean, variance, and covariance. This is how a stationary time series data would look. If we plot a time series data, and if we plot the mean of a time series data, that would be constant like this. If it is stationary, if it is non-stationary, then it would be changing. And we also talked about how to find the moving average, the concept of moving average, how to calculate the moving average, and also in order to get a smoothen the whole thing, we talked about the centered moving average. And this is how, if we plot and visualize, this is how the data would look. This blue color is the actual data, and then the green color is the centered moving average, and the red color is the red colored graph or the line are the predicted values. So with that recap, let's go ahead and implement a time series forecast in R. So in this section, what are we going to do? We are going to use ARIMA model. There are different models and algorithms for performing time series forecasts. So we will use ARIMA, which is the most common one. And we will also talk about what is autocorrelation and partial autocorrelation. And we will see that in RStudio as well. And then we will take you through a use case where we will forecast the air ticket sales for the future. And then we will end with the model validation using the junk box text. Okay, so with that, let's get started. First of all, as I mentioned, we will be using the ARIMA model to do the forecast of this time series data. So let us try to understand what is ARIMA model. So ARIMA is actually an acronym. It stands for Autoregressive Integrated Moving Average. So that is what is ARIMA model, and it is specified by three parameters, which is P, D and Q. P stands for autoregressive, so let me just mark this. So there are three components here: autoregressive, integrated, moving average. Okay, so these three parameters correspond to those three components. So the P stands for autoregressive, D for integrated, and Q for moving average. So let us see what exactly this is. So these three factors are: P is the number of autoregressive terms, or AR, we will see that in a little bit, and D is how many levels of differences that we need to do or differentiation we need to do, and Q is the number of lagged forecast errors. So we'll see what exactly each of these are. So AR is the number of autoregressive terms, and which is basically denoted by the P, and then we have D, which is for the number of times it has to be differentiated, and then we have Q, which is for the moving average. So what exactly AR terms? So in terms of the regression model, autoregressive components refer to the prior values of the current value. Well, what we mean by that is, here when we talk about time series data, focus on the fact that there is regression. So what exactly happens in regression? We try to do something like, if it is simple linear regression, we do some equation like y is equal to mx plus c, where there are two variables. One is the dependent variable, and then there is an independent variable. Let me just complete this equation as well, mx plus c. Right? So this is a normal regression curve or a simple regression curve. Now here we are talking about autoregression or autoregressive. So autoregressive, as the name suggests, is regression of itself. So which means that here you have only one variable, which is your maybe the cost of the flights or whatever it is, right? And the other variable is basically time dependent, and therefore the value at any given time, and that we will denote as yt, for example. So there is no x here, there is only one variable, and which is y, and we say yt, which is basically the predicted value at a time interval t, for example, is dependent on the previous value. So for example, there may be a1 and then yt minus 1, and then there will be like plus a2 and plus a2 and yt minus 2 and alright, and then plus a3 into yt minus 3. Alright, so basically here what we are saying is there's only one variable here, but there is a regression component. So we are doing a regression on itself. So that's how the term autoregression comes into play. So only thing is that it is dependent on the previous time values. So there is a lag, let's say this is the first lag, second lag, third lag, and so on. So the current value, which is yt, is dependent on the previous time lag values. So that is what is autoregression component. So this is what is shown here. For example, in this case, instead of y, we are calling it as x. So that's the same, and this is represented by some equation of that sort depending on how many lags we take. So that is the AR component, and the term P is basically determines how many lags we are considering. So that's the term P for. Now, what is D? D is the degree of differencing. So here differencing is like for the non-seasonal differences, right? So for example, if you take the values like this, which are given for 5, 4, 6 and so on and so forth, if you take the differencing of one after another, like for example 5 minus 4 or 4 minus 5, the next value with the previous value, so 4 minus 5. So this is known as the first order differencing. So the result is -1. Similarly, 6 minus 4 is 2. 7 minus 6 is 1. So this is first order differencing, and here we call it as D is equal to 1. Okay, and same way we can have second order, third order and so on. Then the last one is Q. Q is the actually we call it moving average, but in reality it is actually the error of the model. So we also sometimes represent as ET. Alright, so now ARIMA model works on the assumption that the data is stationary, which means that the trend and seasonality of the data has been removed. That is correct. Okay, so this we have discussed in the first part, what exactly is stationary data and how do we remove the non-stationary part of it. Now, in order to test whether the data is stationary or not, there are two important components that are considered. One is the autocorrelation function and the other is the partial autocorrelation function. So this is referred to as ACF and PACF. Alright. So what is autocorrelation and what is the definition? Autocorrelation is basically the similarity between values of a same variable across observations, as the name suggests. Now, how do we actually find the autocorrelation function, the value, right? So this is basically done by plotting, and autocorrelation function also tells you how correlated points are with each other based on how many time steps they are separated by and so on. That is basically the time lag that we were talking about. And it is also used to determine how past and future data points are related. And the value of the autocorrelation function can vary from -1 to 1. So if we plot, this is how it would look. Autocorrelation function would look somewhat like this, and there is actually a readily available function in R, so you will see that, and you can use that to plot your autocorrelation function. Okay, so that is ACF, and we will see that in our R Studio in a little bit. And similarly, you have partial autocorrelation function. So partial autocorrelation function is the degree of association between two variables while adjusting the effect of one or more additional variables. So this again can be measured and it can also be plotted, and its value once again can go from -1 to 1, and it gives the partial correlation of time series with its own lagged values. So lag again we have discussed in the previous couple of slides. This is how a PACF plot would look in R Studio. We will see that as well, and once we get into the R Studio. And with that, let's get into R Studio and take a look at our use case. Before we go into the code, let's just quickly understand what exactly is the objective of this use case. So we are going to predict some values or forecast some values, and we have the data of the airline ticket sales of the previous years, and now we will try to find or predict or forecast the values for the future years. All right, so we will basically identify the time series components like trend, seasonality, and random behavior. We will actually visualize this in R Studio, and then we will actually forecast the values based on the past values or history data, historical data. So these are the steps that we follow. We will see in R Studio in a little bit. Just quickly, let's go through what are the steps. We load the data, and it is a time series data. If we try to find out what class it belongs to, the data is actually air passengers data that is already comes preloaded with R Studio. So we will be using that, and we can take a look at the data, and then what is the starting point, what is the end point. So these are all functions that are readily available we'll be using, and then what is the frequency. So it's basically the frequency is 12, which is like yearly data, right? So every month the data has been collected. So for each year it is 12. And then we can check for any missing values if there are any. And then we can take a look at summary of the data. This is what we do in exploratory data analysis. And then we can plot the data, visualize the data, how it is looking, and we will see how the data has some trend, seasonality, and so on and so forth. All right, then we can take a look at the cycle of the data using the cycle function, and we can see that it is every month. That's the cycle. End of every 12 months, a new cycle begins. So each month of the year is the data is available. Then we can do box plots to see for each month how the data is varying over the various 10 or 12 years that we will be looking at this data. And from exploratory data analysis, we can identify that there is a trend, there is a seasonality component, and how the seasonality component varies also we can see from the box plots. And we can decompose the data. We can use the decompose function rather to see the various components like the seasonality, trend, and the irregularity part. Okay, so we will see all of this in RStudio. This is how they will look. This is the once you decompose, and this is how you can visualize the data. This is the actual data, and this is the trend. As you can see, it's going upwards. This is the seasonal component, and this is your random or irregularity, right? So we call it irregularity, or we can also call it random, as you can see here. Yes, so the data must have a constant variance and mean, which means that it is stationary before we start any analysis, time series analysis. And so basically, if it is stationary, only then it is easy to model the data, perform time series analysis. So we can then go ahead and fit the model. As we discussed earlier, we'll be using ARIMA model. There are some techniques to find out what should be the parameters. So we will see that when we go into RStudio. So the auto ARIMA function basically tells us what should be the parameters, right? So these parameters are the P, D, and Q that we talked about. That's what is being shown here. So if we use auto ARIMA, it will basically take all possible values of this P, D, Q, these parameters, and it will find out what is the best value, and then it will recommend. So that is the advantage of using auto ARIMA. All right. So like in this case, it will tell us if we use this parameter trace, we set the parameter trace is equal to true, then it will basically tell us what is the value of this AIC, which has to be minimum. So the lower the value, the better. So for each of these combinations of P, D, and Q, it will give us the values here, and then it will recommend to us which is the best model. Okay. Because whichever has the lowest value of this AIC, it will recommend that as our best PDQ values. So once we have that, we can see that we can potentially get a model or the equation. Model is nothing but the equation, and based on the parameters that we get. And we can do some diagnostics. We can do some plotting to see whether there is a plot for the residuals, so which shows the stationarity. And then we can also take a look at the ACF and PACF. We can plot the ACF and PACF, and then we can do some forecasting for the future years. So in this case, we have up to 1960, and then we can see how we can forecast for the next 10 years, which is 1970, up to 1970. And once we have done this, can we validate this model? Yes, definitely we can validate this model. And to validate the findings, we use junk box test, and this is how you just call box.test, and then you pass these parameters, and you will get the values that will be returned, which will tell us whether how accurate this model is, how accurate the predictions are. So the values of P are quite insignificant in this case. We will see that, and that also indicates that our model is free of autocorrelation, and that will basically be it. So let's go back and into our RStudio and go through these steps in real time. So we have to import this library. Forecast package is not installed. You have to go here and install the forecast package. Okay, so that's the easy way to install rather than to click on this install. I will not do it now because I've already installed. So the first time, that's only one time. Then after that, you just have to load it into memory and then keep going. So we will load this data called air passengers. So by calling this data method, and if you see the data air passengers is loaded here, and if we check for the class, it is a time series data, TS data. So we can check for the dates. We can also view the data in a little bit, and the start date is 1949 and January, and our end date is 1960 December, and the frequency is 12, which is like collected monthly. So that is the frequency, which is 12 here, and then we check if there are any missing values. There are no missing values, and then we take a look at the summary of the data. This is all exploratory data analysis, and then if you just display the data, this is how it looks. And then we need to decompose this data. So we will kind of store this in an object TS data and then use that to decompose and store the new values. Let me just clear this for now. And if we decompose, basically, as we have seen in the slides, decomposing is breaking it into the trend, seasonality, and irregular or random components. Then you can go ahead and plot it. So when you plot it, you can see here, let me zoom this. This is our original plot, or observed value as it is known as. Then we have decomposed the three parts, which is basically the trend. As you can see, there is an upward trend. Then the seasonal component. So this is some regularly occurring pattern. And then there is a random value, which is basically you cannot really give any equation or function or anything like that. So that's what this plotting has done. And then you can actually plot them individually as well. So these are the individual plots for the trend, for the seasonal component, and the random component. All right. So now let's take a look at the original data and see how the trend is in a way. So if we do this linear regression line, it will show that it is going upwards. And we can also take a look at the cycle that are there, which is nothing but we have a frequency of 12, right? So the cycles will display that it is January, February to December, and then back to January, February, and so on and so forth. And if we do box plots for the monthly data, you will see that for each of the months, right? And over the 10 years that the data that we have, we will see that there is a certain pattern, right? This is also in a way to find the seasonality component. So while January, February sales are relatively low, around July, August, the sales pick up. So especially in July, I think the sales are the highest. And this seems to be happening pretty much every year, right? So this is every year in July, there seems to be a peak in the sales, and then it goes down and slightly higher in December and so on. So that is again part of our exploratory data analysis. And once again, let's just plot the data. Now, as I said, in order to fit into an ARIMA model, we need the values of P, D, and Q. Now, one way of doing it is, there are multiple ways actually of doing it. The earlier method of doing it was you draw the autocorrelation function plot and then partial autocorrelation function plot and then observe that and where does this change and then identify what should be the values of P and Q and so on. Now, R really has a very beautiful method which we can use to avoid all that manual process that we used to do earlier. So what R will do is, there is a method called auto ARIMA, and if we just call this auto ARIMA method, and it will basically go and test the ARIMA model for all possible values of this parameters PDQ, and then it will suggest to you what should be the best model, and it will return that best model with the right values of PD and Q. So we as data scientists don't have to do any manual, trial and error kind of stuff. Okay, so we got the model now, and this is the model. It has PDQ values are 211 the PDQ, and this is the seasonal part of it, so we can ignore it for now. And so if we want to actually understand how that has returned these values 211 as the best one, there is another functionality or feature where we can use this trace function or trace parameter. So if you pass to auto ARIMA the trace parameter, what it will do is it will show you how it is doing this calculation. What is the value of the AIC? Basically, AIC is what defines the accuracy of the model. The lower, the better. Okay. So for each combination of PDQ, it will show us the value of AIC. So let's run it instead of me talking so much. Let's run this. If we run auto ARIMA with trace, you see here there is a red mark here. That means it is performing. It's executing this, and here we see the display, right? So it starts with certain values of PDQ, and then it finds that value is too high, so it starts with again with some 0, 1, 1, 0, and so on and so forth, and ultimately it tells us, okay, this is our best model. You see here, so it says this is our best model 211. Let's go back and see, did we get the same one? Yes, we got the same one when we ran without trace as well, right? Now why is 211? Let us see, where is 211? Here is our 211, and if you compare the values, you see that 1017 is pretty much the lowest value, and therefore it is saying this is our best model. All other values are higher. So that's how you kind of get your model. And now that you have your model, what you have to do, you need to predict the values, right? So before that, let us just do some test of these values. So for that, you install T-Series. Again, if you are doing it for the first time, you would rather use this package and install and say T-Series and install it, and then you just use this library function to load it into your memory. Alright, so now that we got our model using AutoArima, let us go ahead and forecast and also test the model and also plot the ACF and PSCF. Remember, we talked about this, but we did not really use it. We don't have to use that, but at least we will visualize it. And for some of the stuff, we may need this T-Series library. So if you are doing this for the first time, you may have to install it, and my recommendation is don't use it in the code. You go here and install T-Series, and I will not do it now because I have already installed it, but this is a preferred method. And once you install it, you just load it using this libraries function, and then you can plot your residuals, and this is how the residuals look, and you can plot your ACF and PSCF. Okay, so this is how your PSCF looks, and this is how your ACF looks. For now, there is really nothing else we need to do with ACF and PSCF. This is just to visualize how it looks. But as I mentioned earlier, we were actually using these visualizations or these graphs to identify the values of P, D, and Q. And how that was done, it's out of scope of this video, so we will leave it at that. And then we will forecast for the next 10 years. How do we forecast that? So we call forecast, and we pass the model, and we pass what is the level of accuracy that you need, which is 95%, and for how many periods, right? So basically we want for 10 years, which is like 10 into 12 time periods. So that's what we are doing here. And now we can plot the forecast value. So you see, this is the original value up to I think 62 or whatever, and then it goes up to 72. This blue color is the predicted value. Let's go and zoom it up so that we can see it better. So from here onwards we are forecasting, and you can see that it looks like our model has kind of learned the pattern, and this pattern looks very similar to what we see in the actual data. Now, how do we test our model? So we can do what is known as a box test, and we pass our model here, residuals basically, with different lags, and from those values here, the p values here, we find that they are reasonably low, the p values, which means our model is fairly accurate. Okay, great. So I hope this was helpful, and with this we come to the end of this video. Alright, so with that, we pretty much come to the end of this video. And quick summary, we talked about what is ARIMA model, what are AR, and the D, which is for the degree of difference, and moving average. So the PDQ values we talked about, we briefly touched upon autocorrelation function and partial autocorrelation function, and we saw that in R as well. We plotted and saw it in R. We saw how to implement this in RStudio, and as a part of that we did some exploratory data analysis, and then we did the time series decomposition, and then finally we did the forecast, and then we kind of validated the model as well.
Completing this course, you will be able to get a basic introduction to R, understand exploration of data, explore data using R, visualize data using R, understand diagnostic analytics, implement diagnostics analytics using R, Understand the concepts above with the help of case studies. Let's start our lesson with a basic introduction to R. R has become one of the most popular tools for data mining. Let's see why and also gain some basic knowledge on R. R is a freely available programming language for statistical computations and graphics. It is published under the GNU Public License. It is mainly used in the fields of data mining and statistical analysis. Out of its various applications, it includes time series analysis, linear modeling, and non-linear modeling. The main advantage of using R over other such tools for data mining is its active community, the built-in packages, and the package contributions by the members of the community. Another reason for its popularity is that R needs very little programming knowledge. You can download R from its official website, r-project.org. The website has instructions on how to download and install R and the basic machine requirements. RStudio is an IDE for programming in R that is freely available. It is completely optional for you to download RStudio. The programming in the following chapters will be taught using the R command line prompt. If you are using RStudio, you can type in the same commands as shown in the chapters. Finally, you are strongly encouraged to check the community forums on R as you go through this lesson, to answer basic questions and to explore the different functionalities of R. In the next slide, let's start with a very basic introduction to the commands in R. Before getting into the specifics and statistical analysis in R, listed here are a few important commands that would be used throughout the course. To use a particular package, the install.packages function is used. This installation needs to be done only once. Once installed, the functions can be loaded into the current session by calling the library function. R comes with a set of built-in sample datasets, which we would be using in our lessons. This data can be loaded using the data function, and the syntax is data of dataset name. To use external data, the read function is used. The write function writes data from the R session to a file. R's default directory is the user's documents folder. It can be verified by using the getWD function. To change the working directory, use the setWD function with the full path name as the argument. In case the working directory is not set, the full path name needs to be specified for read and write functions. For example, read.csv of c:/r tutorials/sample-data.csv. Note that R uses the / for specifying directories. The assignment operator in R is different from the equal to operator. To assign a value to a variable in R, use the lesser than dash symbol. For help on any function in R, type ? followed by the function name to open the R help text. If you are using R, the help text will open on the default browser. In the next slide, we will look at the basic exploration using R. Before getting into the functions and commands for data exploration, let's look at how data is stored in R. The data in R is stored as data frames, which are a tabular representation of the rows and columns. There are other types of data as well, including table, matrices, vectors, and single values. In our course, we will primarily use data frames and time series data in the later chapters. In the slide, you can see a sample data frame. The IRIS dataset is a very popular, commonly used dataset introduced by Sir Donald Fisher. The data contains 150 entries belonging to 3 different species and includes features such as sepal length and width, and petal length and width. The 3 species have 50 entries each, as shown in the data frame. Each row denotes a particular case, or in this context, features of a particular flower. The column denote the different attributes measured. In the next slide, we will look at different commands to view data. Let's start with basic commands to view data in R. Throughout this lesson, we will look at commands and screenshots of R that will display a sample output. You are encouraged to pause the video and try out the commands on your command prompt for better understanding. The IRIS dataset is loaded by default in R. To view the dataset, just type the dataset name on the prompt. To view the top few records, use the head function. The syntax is head of dataset name, comma, number of rows. The number of rows is an optional argument, and the default number of rows is 6. To view the last few records, the tail function is used. The syntax is similar to the head function. Tail of dataset name, comma, number of rows. In the next slide, we will look at commands to view the dimensions of data. Listed here are a few commands to view the dimensions of a dataset. Dim of dataset name gives a vector result of the number of rows followed by the number of columns. Encol of dataset name gives the number of rows, and nrow of dataset name gives the number of columns separately. Try these commands with the sample IRIS dataset. In the next slide, we will look at the attributes of the data frame. To view the column names of a particular dataset, type names of dataset name. To view all attributes, type attributes of dataset name. Given here is a snapshot of the 2 commands of the IRIS dataset. You can see that the column names are displayed as strings in the first output. Attributes displays the column names, row names, and the data type of the dataset. The class command is used to display the data type of the argument. The syntax for class command is class of variable name. For example, class of iris would be data.frame. To know the type of a particular column, type class of iris $sepal.length. The $sign is used in referencing the columns of a dataset. In the next slide, we will look at viewing columnar data. To view data of a column, the following 2 notations will be used. As mentioned in the previous slide, dataset $column name would display the particular column. Another way is to use a matrix form, that is, dataset of space, comma, column name. Instead of the column name, the column number could also be used. In this case, petal length is the 3rd attribute, hence iris of space, comma, 3 would also give the same result. In the next slide, we will discuss viewing row-wise data. Similar to columns, data of Particular rows can also be viewed using the square brackets. The format is dataset name of row numbers, comma, space, to display all columns, or dataset name of row numbers, comma, column name, or numbers, to display particular rows of particular columns. You can see the screenshot for the subsets using square brackets on the iris dataset. Also note, if a single column or row is displayed, the output is in default vector form. This concludes viewing data and exploration in R. You are advised to try out all these commands on your R or RStudio for better understanding. Next, we will look at a video to illustrate the commands we have used so far. This video shows all the basic operations that can be performed on R and will help any layman to use R efficiently. We start off with one of the very basic operations that help us to load and install any package that is not pre-installed in the R workspace. Step 1. This operation is called install.packages, with the package name within double quotes. Step 2. A pop-up opens that asks for the server to which you should connect to download the package. Zero Cloud at the beginning is enough to download the package. Selecting that and clicking on OK downloads and installs the package. Step 3. Then the package needs to be loaded onto the workspace, which we do by using the library function. Once that is done, the features of the package can now be used for our purpose. Step 4. Next, we try to load a dataset that will be frequently used for all the analysis that follow. This is the iris dataset, and you load it using the data function. Data of iris loads the iris dataset onto the workspace. Step 5. Now we shall do some basic analysis on R. Just to note that before doing any analysis, it is safe to save the dataset onto the workspace that we try to use by using the attach function. So attach of iris will save the dataset onto the workspace. Step 6. Once done, we can remove it from the workspace by using the detach function. That is, detach of iris will remove the dataset from the workspace. Step 7. First, we load the dataset into a user-defined variable, say, my data, using the assignment operator less than dash, which is less than sign followed by a hyphen. We can also use the equal sign instead. Both work the same way. Step 8. Now that the data is loaded into the user variable, we can check the structure of the data using the head function. Entering head of my data returns the first 6 records of the dataset. Step 9. Now the screen is pretty full and we would like to clear it. A keyboard shortcut comes in handy at this point, and that is Control-L, which clears the screen of the current workspace. Step 10. Next, we look at how to check and change the current working directory. The function getWD returns the current working directory we are in, and the function setWD helps in changing the working directory, which we pass as argument to the function within double quotes. The next function that we are going to look into is the read function in R, along with the type of files that can be read. Step 1. Read.csv helps us to load a CSV file, the path for which we need to pass as argument to this function. We load the dataset stored in the file into a user variable, and then check the structure using the head function. Step 2. We can even make a data frame of this data by using the data.frame function and passing the read.csv as an argument, or we can even pass the user variable that stores the data as an argument. Step 3. Just like the head function, we have the tail function that shows the last 6 records of a dataset. Tail of the dataset returns those records. Step 4. We can display as many records by passing the required number as an argument after the dataset name. So, head of my data, followed by a comma, and then the number of records you want to view returns those records, many from the start of that dataset. Next, we check 4 more basic functions of R, namely dim, encall, enrow, and names. Step 1. The dim function returns the dimensions of the dataset. That is, the total number of rows and columns. Run the command dim of dataset name to get the required result. Step 2. The encall function returns the total number of columns, and the enrow function returns the total number of rows in the dataset. Run the commands encall of dataset name and enrow of dataset name to get the corresponding results. Step 3. Lastly, the names function returns the title of all the columns that are there in the dataset. As usual, run names of dataset name to get the column names. Data manipulation. Moving on to viewing row and column data, the following techniques are possible. Column data can be viewed in 3 different ways. First technique. Call the column name after the dataset name using the $sign. That is, dataset name $column name. Second technique. Call the column name as a matrix attribute of the dataset. That is, dataset name, then within the square brackets, enter comma followed by the column name with double quotes. Third technique. This is similar to the second technique, with the difference that in place of the column name within the square brackets, we need to enter the column number. Row data can be viewed in the following way. Enter the row number, followed by a comma within square brackets after the dataset name. We can view multiple rows by entering the first and last row of our choice, separated by a colon. In the next slide, we will look at the summary functions. The summary function is a generic function in R that displays summaries of data or models, as we will see in later chapters. The syntax is summary of dataset. As shown in the screenshot, the summary function displays the minimum value, maximum value, mean, median, and first and third qualities of every numeric data. For categorical data, like species, it displays a table of the different values and their frequencies. The table can be displayed separately by giving table of data frame $column name. Look at the example. Table of iris $species displays a frequency distribution of the 3 different classes. Note that summaries for individual columns can also be obtained by using the summary function and giving the referenced column name as an argument. For example, summary of iris $sepal.length would display the results of sepal length column alone. In the next slide, we will look at a list of commands for the individual summary statistics. The summary function displays all the summary statistics for a particular data. Here you can see a list of commands to display individual summary statistics. The argument for each function is the column name for which the statistics is to be obtained. The commands are min to get the minimum value, max to get the maximum value, range to get the range of the data. That is, maximum minus minimum value. Mean to get the average value. Median to get the median or middle value. IQR to get the interquartile range of the data. That is, the difference between the first and third quartiles. SD to get the standard deviation. VAR to get the variance. In the next slide, we will look at ways to aggregate data in R. Next, we use the summary function of R to get an overall snapshot of the whole data set. Step 1. Summary of the dataset name returns the mean, median of each numeric column, and the frequency of levels of every categorical column. There are various other functions that can be used to separately analyze all the columns in the dataset. They are as follows. Step 2. Min. Min of column returns the minimum value in that column. For example, when we do a min of the sepal length column of the iris dataset, we get the value 4.3, which is the lowest value in the column. Step 3. Max. Max of column returns the maximum value in that column. For example, when we do a max of the sepal length column of the iris dataset, we get the value 7.9, which is the highest value in the column. Range. Range of column returns the range of values in that column. For example, when we do a range of the sepal length column of the iris dataset, we get 2 values, 4.3 and 7.9, which tells us that the values in the column lie between these 2 extremes. Step 5. Mean. Mean of the column returns the average of all the values in that column. For example, mean of sepal length returns the value 5.8433, which is the average of all the values in sepal length. Step 6. Median. Median of a column returns the central value of by position in that column. For example, median of sepal length returns the value 5.8, which is in the middle of all the values in that column. Step 7. IQR. The IQR of a column returns the interquartile range of that column, giving us a sense of the difference between the upper quartile and lower quartile of the values of that column. IQR of the sepal length returns the value 1.3. Step 8. Standard deviation. The function SD is used to find the standard deviation in a column of the dataset. For example, SD of sepal length returns the value 0.8280661. Step 9. variance. To find the variance in R, we use the var function. So var of sepal length returns the value 0.6856935. Having finished all the basic statistical function in R, we now move to aggregating the dataset at hand. Aggregating the dataset is one of the few important data manipulation functions in R. Parameters that need to be passed into the aggregate function are formula for the aggregation, dataset used, and the type of aggregation. That is, a mean aggregation or a sum aggregation. Aggregation in R can be done using the aggregate function in two ways. The two ways differ only in the formula that is used for the aggregation. Step 1. In the first way, we do it across the dataset by a particular column. Like the iris dataset, we can aggregate across the dataset by species. Step 2. For this scenario, we enter the formula as dot tilde followed by the column name, which is species in our case. The enter data equals iris for specifying the dataset, and last give the type of aggregation, that is mean or sum. Step 3. In the second way, only the formula differs such that the aggregation is not done across the dataset, but only on the variables or columns used in the example. With this, we come to the end of the basic operations that can be performed in R, right from data viewing to data manipulation to basic statistics. Next, we'll focus on the visual aspects of R. In the next slide, we will look at the functions to visualize data in R. The aggregate function is used to group data values of a particular column. The compulsory arguments are the formula for aggregation and the function for aggregation. The first argument aggregates all the columns, as denoted by the dot symbol, grouped by the value of species. The next argument mentions that the data belongs to the iris dataset, and the last argument specifies that the aggregation should be done by averaging the values. You can see the result has 3 rows, 1 for each class, and the mean values for each column. The second command aggregates only the sepal length column by species, belonging to the iris dataset. In addition to the mean function, the sum function is a commonly used statistic in aggregation. You can see the other available functions by typing a question mark followed by aggregate to see the help content. Next, we will look at a video that illustrates summary statistics. Plot is a generic function used for plotting data in R. The function can be used to plot a variety of graphs on a variety of data, including data frames, time series, and even vectors. The plot function creates a scatter plot by default. Other plots can be created using the type attribute. You can check the help section for more details on the plot function. Shown here is a plot of iris data. On plotting the data frame, it creates a pairwise data plot for all the attributes in the data frame. In the next slide, we will look at a simple scatter plot. The plot function can be used to create scatter plots of one variable against another. For example, let us plot sepal length against species. We will use a few optional attributes of the plot function. Main, to specify the title of the plot. xlab, the x-axis label. ylab, the y-axis label. The function would now be plot of iris $sepal, dot length, comma, iris $species, comma, main equals iris data, comma, xlab equals sepal length, comma, ylab equals species. The output plot is shown on the right. From the scatter, it is easier to notice the differences in the sepal length according to species. Next, we will look at pie charts. Pie charts are the simplest form of visualizing the numerical proportion of the different classes through the sectors of the circle. The pie function is used to create pie charts in R. The table function is used to create a frequency table, and then the pie function is called to create a chart of the table. The main attribute, as mentioned before, is used to specify the title for the chart. Here is an example chart showing the different species of iris data. The circle is divided into 3 equal sectors for the 3 species. In the next slide, we will look at bar charts. Bar plots are used to depict values in vertical manner, with the height being equivalent to the value that's being shown. For this example, we will use another built-in data set, U.S. Personal Expenditure. The data set is displayed in the table. It displays the personal expenditure data for categories across years 1940 to 1960. In R, bar plots can be created using the bar plot function. As with the plot function, the main, xlab, and ylab attributes can be used for labeling. This slide shows an example function to create a bar plot using the expenditure data, and on the right, the created bar plot is shown. In the next slide, we will create box plots. Box plots are used to show numerical data with their quartile ranges, also called a box whisker plot. The boxes show the interquartile region, with the middle line equal to the median. The whiskers show the lower and upper quartiles, and the points show the outliers. The box plots are very useful in detecting the outliers. In R, box plots can be created using the boxplot function. Let's see the example function displayed on the slide. The first attribute shows the features to be plotted. That is, sepal length against the species, the data, and the labeling information. On typing this into the R prompt, you will get a graph similar to the one shown on the slide. You can see that there is an outlier in the Virginica species. In the next slide, we will look at histograms. Histograms are used to depict frequency distribution data. R has a default islands dataset that is best suited to create histograms. Once you are done with this slide, you are encouraged to try creating a histogram using the islands data. In R, histograms can be created using the hist function. The first attribute gives the vector or data frame to plot, and the usual labeling attributes can be used to label the plot. It can be seen from the plot that the sepal length is mostly concentrated around 4.5 to 6.5. For numerical data such as sepal length, the data is put into buckets and the histograms are created. This slide concludes data visualization. In addition to these attributes, plots can have other attributes such as X and Y axis limits, colors for points or bars or lines, etc. They can be found in the Help section for each plot. Next, we will look at a video that helps in understanding the different commands used in visualizing the data. Basic data visualization in R can be done using the plot function. Step 1. When we do a plot of the iris dataset, a separate window pops up showing a scatter plot across each and every variable of the dataset. Step 2. If we want a plot of any particular variable or set of variables, then we pass the variable or column names as argument to the plot function. For example, for plotting the sepal length across species, we give the sepal length and species as the arguments, separated by a comma. Here, the first argument is the x-axis argument for the plot, and the next argument is the y-axis. Step 3. Next, we can generate a pie chart in R using the pie function along with the table function. In our case, we use the species column of the iris dataset and pass it through the table function to get a frequency table of all the species, which is then used to generate the pie chart. So we enter the pie of table of species and get the pie chart as output. Step 4. Further, we use the bar plot function to generate the bar plot chart, and in our case, similar to the pie chart scenario, we enter bar plot of table of species to get the bar plot chart. Now, for the box plot function, we need to pass a formula specifying the variables that are required to be plotted. Say, for example, sepal length tilde species, and along with that we enter the data equals iris separated by a comma, and then try to generate the required box plot. Step 6. The final basic visualization function that comes to use is the histogram plot generated using hist function. The basic argument that needs to be passed is the variable that we want to plot. In our example, we just need to pass, say, the sepal length, and we get a histogram plot. We can fine-tune this plot by passing the main chart title, x-axis, titled, and y-axis titled using the main xlab and ylab arguments in the plot function. And this can be done in case of all other plots. In the next slide, we will look at a case study to understand what we have learned so far. Let's now take a banking-related data set as an example for doing data exploration. Officer David from the sales department has been asked to do a study on the overall performance of a bank by analyzing the bank loans. As part of the investigation, David has asked his colleague to categorize the loans as seasoned or bad loans with respect to age category. The following data categories have been captured: age group, total number of loans, number of good loans, number of bad loans, percentage of good loans, percentage of bad loans. In the next slide, we will have a look at the data. Here you can see a table of the bank loan data. As mentioned in the previous slide, the number of good loans and bad loans has been tabulated as per the age category. There are 15 categories of age in the table. Given the total number of loans and the number of good and bad loans, the percentage of good and bad loans has been tabulated. In the following video, we will look at different statistics and graphical visualizations for the data. Let us start by exploring the data. Since it is a preloaded dataset in R, we will not be using any read command. However, if you wish to save it to an Excel file, use the write.csv command. The write.csv command takes two arguments: the data frame name and the name of the file you wish to write it to. For example, .csv of empty cars, comma, motor trends car data .csv creates a file motor trends car data in the current working directory with the given data. Step 1. First, let us view the data set. Type empty cars to display the whole data set. We learned the concept of data frames earlier. Let us find the class of the data set in R. Type class of empty cars and hit enter. From the output, we can infer that the data is stored as a data frame. Step 2. Let us confirm the number of columns and rows in the data set. Type dim of empty cars. The output shows 32 and 11 separated by a space, implying that there are 32 rows and 11 columns. Step 3. Let us explore the data in detail. Use head of empty cars to display the first 6 rows. Though we already established the types of the variables, let us confirm it by looking at this data. We can see that VS and AM have either 0 or 1 values, and thus have been rightly classified as categorical data. The number of cylinders, gears, and carburetors has discrete numerical values, and the rest of the data are in continuous numeric format. Step 4. To look at all the types of cars, type attributes of empty cars and press enter. The first section gives the column names, which we have already discussed. The second section has row names, which consists of the model names of all 32 cars. Finally, the class of the variables displayed, that is, data frame. Step 5. Let us find what all values that the variable number of gears can take. Type empty cars $gear. All the values of the column are displayed. You can see that the values 3, 4, and 5 are repeated in the data set. Similarly, you can check the number of cylinders and carburetors too. Step 6. Suppose you would like to know the attributes of a particular car. For example, the Ferrari Dino. We will use the format to view the row data here. Type empty cars of Ferrari Dino and a comma within square brackets and press enter. You can now see the attributes of Ferrari Dino displayed in a single row. Step 7. Now that we have explored the data, we will now look at summarizing to get some meaningful insights. Before doing this, let us first convert the data type for versus and AM to factor. They are numeric by default. To convert the data type, use the as.factor command. Type empty cars $AM equals as.factor of empty cars $AM. Do the same for the versus variable as well. Step 8. Getting into the summarizing part, as seen earlier, type summary of empty cars to display all the summary statistics. From the first section, we can infer that the maximum miles per gallon is 33.90, and the average is 20.09. The minimum miles per gallon is displayed as 10.40. Similarly, we can note the maximum, minimum, and other statistics for the rest of the numeric data. For the categorical data, the number of entries in each group or category is displayed. For example, from the AM column, it can be inferred that out of 32 cars, 19 are automatic and 13 are manual. Step 9. What if we need to know which car among the 32 gives the best mileage? The which.max function is used to return the index of the maximum value in the data set. For example, type empty cars of which.max of empty cars, $MPG, and a comma. The which.max returns the index of the maximum value for MPG variable, and attaching that with the empty cars variable displays the row with the maximum value for mileage. You can see that Toyota Corolla has the maximum mileage in the given set of cars. Step 10. Similarly, the row with the minimum value can be found using the which.min function. Let us find the lightest car in the given set of cars. Type empty cars of which.min of empty cars $WT and a comma. We now know that the Lotus Europa is the lightest of the cars. Step 11. The commands mentioned now can thus be used to find the maximum or minimum of any variable and the corresponding car data. You are encouraged to try different combinations to get meaningful insights. Step 12. As a final exploration technique, let us try the aggregate function. Suppose we would like to know the average mileage of cars that have 3 gears. We will use the aggregate function to aggregate the MPG variable by the variable gear, and the aggregation function would be average. Type aggregate of MPG tilde gear, comma, data equals empty cars, comma, fun equals mean, and press enter. The output consists of 2 columns, the number of gears and the mean of the mileages. We can infer that the cars with 3 gears have a mileage of 16 on average. The cars with 4 gears are the best in terms of mileage, giving the highest average mileage. The aggregate function can similarly be used to find the average speed of manual and automatic transmission vehicles, and so on. Following mathematical exploration techniques, we will now visualize data and try to support the inferences made through the earlier commands. Step 1. Let us start with a scatter plot that includes all the factors in the dataset being plotted against each other. Type plot of my data and hit enter. The new window shows a plot with all the variables plotted against every other variable in the dataset. Step 2. But this gives a very generic plot of all the variables, and it is hard to make any useful inferences from this plot. Suppose we want to know how the horsepower is related to the displacement. Let us use the plot function with the formula HP tilde disp to get the corresponding plot. We can infer from the scatter plot that the horsepower increases even though gradually as the displacement increases. You can see one data point that might occur as an outlier. The horsepower is quite high for a large displacement vehicle. This shows that there are other factors that have an effect on the horsepower. Step 3. Let us perform a similar plot for the number of cylinders versus the mileage. The formula for the plot function will be MPG tilde sil. You can see the number of cylinders are 4, 6, and 8. And as the number of cylinders increases, the mileage decreases, and the effect is quite visible. This plotting can be done across every combination of variables, and such inferences can be obtained. Though it is statistically possible to create plots for any 2 variables, during a case study, it is advised to understand the data before plotting them. For example, a plot of employee ID versus age in an employee database will work in R, but will not help the researcher in getting any meaningful insights since they are logically unrelated. Step 4. Let's work on the categorical variables. We have the AM variable, which has 2 values, 0 for automatic and 1 for manual transmissions. The summary statistic will show us the number of automatic and manual cars. But if we have thousands of data, it will be difficult to obtain a ratio of the 2 categories. You can graphically view the ratio using the pie charts, as seen in the previous lessons. We will use the pie function. We will create a table of the AM variable using table of empty cars $AM and pass it as an argument to the pie function. From the chart, it is seen that almost 60% roughly are automatic cars in this case. Step 5. Okay, now let us do a very simple pie chart plotting. Let us consider plot for AM data. AM is for automatic or manual property of cars. So if it's needed to find if number of automatic given by 1 is more or less than number of manual, this simple plot can be done. So type some name of the data frame, say auto, to extract the data of AM in the data set of empty cars. So type equals empty cars $AM. Then it's needed to make a table. So make another data frame to assign table for auto. Then for the pie plot, type pie of matic. And now, from the pie plot, it's evident that the number of manual is more than the number of automatic. Step 6. Similarly, create a pie chart for the number of gears. Here, the table should be created for empty cars $gear and passed the pie function. We can infer that almost half of the cars have 3 gears. The other half is distributed between 4 and 5 geared automobiles, with the cars having 5 gears being the least number. Step 7. The continuous variables can be viewed using box plots, as we have seen earlier. Let us create a box plot of the horsepower, grouped by the number of cylinders. The formula for box plot will hence be HP ~sil, and mention data equals empty cars and pass them as arguments for the box plot function. You can see that the horsepower increases as the number of cylinders increase. For cars with 8 cylinders, there is a lot of variation, as can be seen from the wider box and whiskers for the plot. Out of the 3, cars with 6 cylinders have very less variation, though there seems to be an outlier as seen by the dot in the graph. It can also be seen that the median or horsepower for cars with 4 and 6 cylinders do not differ much. Step 8. Let us look at a few bar plots and try to make sense of the graphs. Suppose you want to know the number of cars grouped by the number of gears. To know this, use table of empty cars $gear to create a table of the counts, and pass this as an argument to the bar plot function. From the plot, we can find that maximum number of cars, that is, 15 cars have 3 gears, and 12 cars have 4 gears, and 5 cars have 5 gears. Similarly, this can be done for the number of cylinders. Type bar plot of table of empty cars $sil to view the plot. Here we can see that most cars in our data set have 8 cylinders, and the least cars have 6 cylinders. This inference from the bar plot can be done for all discrete grouping factors. Step 9. As a final descriptive statistic, let us make a histogram plot for the horsepower of the cars. To display the histogram, type hist of empty cars $HP. The histogram divides the horsepower into buckets of 50 units, starting at 50 and ending at 350, thus having 6 bars. We can see that most cars fall into the 100 to 150 horsepower range, and only 2 cars have horsepower of above 250. This concludes the case study on descriptive statistics using R. In the next slide, we will discuss, let's look at the function to test the correlation between 2 variables. Correlation is a class of statistical relationship between 2 variables that forms any form of dependence. For example, Is there a correlation between the height of parents and their offspring? In the example given, we try to find if there is a correlation between the sepal length and width of a flower. In R, correlation can be calculated using the core.test function. By default, the function calculates the Pearson's correlation coefficient. Let's look at how to interpret the results. The output shows the correlation method used and the data. The important output for this test is the p-value, which is calculated using the t-statistics and degrees of freedom. As seen in earlier chapters, if the p-value is less than 0.05, we can conclude that the null hypothesis is rejected. That is, there is no correlation between the two variables. The correlation coefficient is given as 0.1175698. This means there might be a negative correlation between the two variables. But since the p-value is quite high, we conclude that the result is not significant. That is, the correlation is almost zero. Next, we will look at a video to understand correlation using R. In this video, we perform a correlation test on two variables on a dataset to ascertain the significance of the relation and values of the variables. We will use the anorexia dataset from the mass package for the correlation. Load the package by typing library of mass. Specify mass in capital letters. We will use two variables of the dataset to perform the test. That is, pre-WT and post-WT. Run the command core.test of pre-WT and post-WT separated by a comma. The output shows name of the test, that is, Pearson's product moment correlation, in this case followed by the t-value, degrees of freedom, and the p-value. Then it tells you about the alternate hypothesis, which in our case is the true correlation is not equal to 0. Next it shows the 95% confidence values of the correlation, and finally, the mean of the correlation values. In the next slide, we will look at a correlation case study. In this slide, let's look at a case study to illustrate the concept of correlation. The business case we have chosen is about an ice cream company which maintains a database containing total sales per day and the corresponding temperature each day. Given this data for a period of 1 week, the management wants to find whether temperatures is a factor that causes difference in their sales. Looking at our data set, we can infer that there are two variables, sales and temperature. Here, sales represents the value of total sales that happens in the ice cream company each day. And temperature represents the temperature that is being recorded for the corresponding day, measured in Celsius. We will be using correlation to check whether there is any relationship between sales and temperature for this company. And the following video will walk you through the process. Firstly, save the data into a CSV file. Step 1. Import the file in R. As seen earlier, use the read.csv command to read the CSV file with the file name given as arguments. Step 2. Save the dataset in R as My Data. Step 3. To check for the data in the dataset, type My Data and press Enter. The data will be displayed, and you can check if the data has been stored properly. The data will have 7 entries across 2 columns. Step 4. Before working on My Data, attach the dataset My Data to the session by typing Attach of My Data. Step 5. The correlation coefficient is now determined by using the command core.test. We need to supply the variables as arguments, so type sales, comma, temperature within parentheses and hit enter. Step 6. The correlation result is displayed. It can be inferred that the Pearson's product moment correlation test has been performed. The test can be changed by using the method attribute. The t-value for these 2 variables is calculated as 6.6333. The degrees of freedom is 5, and the p-value is given as 0.001173. The basic alternative hypothesis is displayed, and the 95% confidence interval is calculated and displayed. Pearson's correlation coefficient, RHO, is displayed in the last line and equals 0.9476071. From the earlier lessons, we know that a positive sign in the correlation coefficient implies they both are positively correlated. That is, an increase in temperature leads to an increase in sales. The value is close to 1, which suggests that the association between the 2 variables is very strong. In the next slide, we will discuss analysis of variance. ANOVA is used to compare the means between different groups. Here, we show a simple example of one way, ANOVA. To illustrate this, we use the insect sprays data set. This data contains the insect count after using 6 different sprays. Here, the null hypothesis would be that there is no difference in using different sprays. AOV takes the first attribute as dependent variable and independent variable, separated by tilde. Here it is AOV of count spray. The data attribute specifies where the data is to be taken from. After fitting the AOV model, the summary function is used to display the result. It can be seen that the p-value, that is the last column, is lesser than 2e minus 16, which is the least positive number represented by r. Since p-value is almost 0, we can reject the null hypothesis, and thus the inference is that there are differences in results on using different insect sprays. Next, we will look at a video that shows how to perform ANOVA in R. Now, let us perform ANOVA in R using the insect spray dataset. For ANOVA, a model needs to be fitted where we have to decide on a target variable and one or more independent variables. Step 1. In our case, let's take count as the target variable and spray as the independent variable. Step 2. For fitting the model, use the AOV function and save it in a user-defined model name, say fit. So fit equals AOV of count tilde spray followed by passing the data, that is insect spray, separated by a comma. Step 3. To check the model details, run the command fit. Step 4. The result shows a table containing 5 major columns that are in order: degree of freedom, sum of squares, mean squared error, f-value, and p-value for each of the independent variables used in the model. Finally, the significance of the variables can be checked from the p-value in the table, and the important variables can then be used for further advanced modeling. In the next slide, we will look at a case study. Let's look at a case study for better understanding of ANOVA. A pharmaceutical company has tested 3 formulations of a body pain medication for athletes. 27 volunteers were selected, and they were split into 3 random groups. 9 members were assigned randomly to each of the medications. The athletes were instructed to take the medication while experiencing body pain and then report the pain on a scale of 1 to 10. 10 being too much of pain. Here, the table shows the pain rating for each athlete across each medication. The question the company wants to answer is there a significant difference in the effect of the different medications? Since there are more than 2 different groups, we will use analysis of variance to test the significant differences between means of all 3 medications. And the following video will walk you through the process. To start with, save the data into a CSV file. Step 1. Import the file into R. Let's name the file as MyData. To read the file, type MyData equals read.csv of the file name within brackets. Make sure the file is in the current working directory, and if not, type the absolute path of the file with forward slashes to separate the directories. Step 2. Check if the data has been imported by typing MyData to display all the data. Alternatively, you can use head of MyData to display the first 6 rows. Step 3. To apply R's ANOVA function, the data has to be in a single vector format. To do so, let us first convert the 3 columns of data into a single vector. Use the C function to do the conversion. After attaching the data to this session, that is, using attach of MyData, type C of med _1, comma, med _2, comma, med _3. Save it in a variable. Let us name it pain rating. Now type pain rating to see if the vector has been properly stored. Step 4. Now the medication type for each entry data needs to be specified. Create a vector that consists of the value medication 1 for the first 9 entries, medication 2 for the next 9, and medication 3 for the last 9 entries. Let us save it in a variable called types. The rep function can be used to repeat a given string for a given number of times. For example, rep of medication 1, comma, 9 will create a vector that has medication 1 repeated 9 times. To create the types vector, type C of rep of medication 1, comma, 9, comma, rep of medication 2, comma, 9, comma, rep of medication 3, comma, 9. You can now type types on the prompt to check if the vector has been created properly. Step 5. Finally, a data frame has to be created that contains the medication type and its corresponding pain rating. Let us save the data frame in a variable called body pain rating. Type body pain rating equals data.frame of pain rating, comma, types. You can see the data frame by typing body pain rating to view the whole data frame. You can notice that this frame contains 2 columns, pain rating and types, and consists of 27 rows. Now we have the data frame ready. Step 6. Before using ANOVA, let us visualize the data in a graphical format. We will be using the plot function to plot the ratings as a function of the medication type. Type the command plot of pain rating, tilde, types, comma, data equals body pain rating, and hit enter. The box plot of the ratings is displayed in a new window. Note that there is an outlier on the medication 2 rating entries. It can also be noted that the median for medications 2 and 3 are the same, and the median for medication 1 is significantly lower than the other two. Let us now get back to the command prompt. Step 7. As seen in the earlier video, the AOV function is used to perform analysis of variances on the data. The formula for AOV function should be pain rating tilde types, which implies that the grouping is done per the types column. Let us save the result into a variable named ANOVA result. Type ANOVA result equals AOV of pain rating tilde types comma data equals body pain rating. To view the results, we use the summary function. Type summary of ANOVA results to see the results of the test. Step 8. From the previous results, you can see that the value of F statistic is 11.91, with a p-value that is equal to 0.003. Since the p-value is significantly lower than the standard value of 0.05, we can infer that the null hypothesis needs to be rejected. In the context of this study, we can conclude that different medication formulations have different impacts on the pain rating for athletes. In the next slide, we will look at the chi-squared test is used to calculate the goodness of a particular fit. It compares the observed values against expected values obtained from a null hypothesis. Here, we try to test the sepal length for goodness of fit. The low p-value suggests we can reject the null hypothesis. We will now look at a video to understand how to perform a chi-squared test in R. Now we go about doing the chi-square test. For this test, we need a categorical data set, and R has that kind of data pre-installed in it. The data set is called hair eye color. Step 1. Call that data set using the data function. Run the data of hair eye color, and it becomes active in the workspace. Step 2. To handle the data more efficiently, save it in a user-defined variable, say, my data, and put it in a data frame. Step 3. Then do a head of my data to have a look at the data set. Step 4. Just to make things a little more flexible, attach the newly made data set, my data, to the workspace. Step 5. After clarifying the structure of the data set, do the chi-square test. Step 6. Next, for doing the chi-square test, we select two variables from the data set, say hair and eye, and run the command kisc.test of hair, eye. After running the test, we find that these two variables are not at all related and have no significance between each other, suggested by the p-value, which is equal to 1. Step 7. Hence, we move on to choose another set of variables and take hair and freak for the test. This time, we find there is some amount of significance between these two variables, suggested by the p-value, which is equal to 0.06, very close to the 0.05 significance level, which is generally used as benchmark. In the next slide, we will look at a case study. Pairwise t-tests are used to check if there is any difference in paired values. For example, marks obtained by a student before and after a training. To illustrate this, the anorexia dataset from the MASS package is used. The data contains pre-treatment and post-treatment weights of patients. To implement it in R, type t.test of PRUT, post WT, paired equals true. The first two attributes are the features to be compared, and the attribute paired equals true specifies that it is pairwise t-test. The low p-value suggests that the null hypothesis can be rejected. That is, there is a difference between the weights before and after treatment. In the next slide, we will look at independent t-test. The independent t-tests are used in comparing two values where the value of one variable is not directly related to the other variable. For example, marks of students in two different schools. Here we implement a t-test on the sepal length and sepal width of the iris data set. From the result, it can be seen that the p-value is almost zero, and hence the null hypothesis that there is no relation can be rejected. Now we will look at a video that shows how to perform t-tests using R. Next, we try to see how to do t-tests in R. Starting off with the one-sample t-test, use the anorexia dataset for this purpose. Step 1. Choose any variable of the dataset to perform the test, say pre-WT. Step 2. Run the command t.test of pre-WT and pass the parameter mu equals 3 separated by a comma. The mu parameter corresponds to the null hypothesis. Step 3. The output shows name of the test, which is one sample t-test, followed by the t-value, degrees of freedom, and the p-value. Step 4. Then it tells you about the alternate hypothesis, which in our case is the true mean is not equal to 3, since we passed 3 as the value for the mu parameter in our test. Step 5. Next it shows the 95% confidence values of the variable, and finally the mean of the values of the variable. Next we do the independent t-test, also known as the two-sample t-test. Step 1. Choose any two variables of the dataset to perform the test, say pre-WT and post-WT. Step 2. Run the command t.test of pre-WT and post-WT separated by a comma. Step 3. The output shows name of the test, that is, Welch 2 sample t-test, followed by the t-value, degrees of freedom, and the p-value. Step 4. Then it tells you about the alternate hypothesis, which in our case is true difference in means is not equal to 0. Step 5. Next it shows the 95% confidence value of the combinations of the variables, and finally the means of the values of the variables. Now we will do the pairwise t-test. Step 1. Choose any two variables of the dataset to perform the test, say pre-WT and post-WT. Step 2. Run the command t.test of pre-WT and post-WT separated by a comma followed by the paired parameter, which must be entered as equal to true. So to tell the test that you are trying to do a pairwise test. Step 3. The output shows name of the test, that is, paired t-test, followed by t-value, degrees of freedom, and the p-value. Step 4. Then it tells you about the alternate hypothesis, which in our case is the true difference in means is not equal to 0. Step 5. Next it shows the 95% confidence values of the combinations of the variables, and finally, the mean of the difference in corresponding values of the variables. In the next slide, we will look at a case study. A construction company took a project of building luxury residential apartments in Phoenix City. The project head, Andrew, decided to make an analysis on other residential apartment constructions nearby Phoenix in order to avoid management difficulties and to easily compete with their competitors. So he asked his colleagues to collect all relevant information that helps him in finding useful insights. He wants to find all the business insights possible so that he can compete with all other competitors, and also avoid taking much risk in terms of decision-making and investments. His colleagues started collecting relevant data. For this, he did a survey of various construction sites in and around the locality. The final data that he collected contained information on 12 variables: ID, local price, bathrooms count, area per square feet, living space per square feet, garage count, rooms count, bedrooms count, age in years, selling price, material, and level. Let us assume that you are the analytics expert in the company and have been assigned the task of working with the data to get insights. Now, we have the data gathered and ready for analysis. The first step that needs to be followed is to import the data into R. For the purpose of analysis and easier access to the data, we will store this data in a time frame and name this data frame as MyData. So, type MyData equals read.csv and give the path for the file. We will see the first 6 data entries and check if we have chosen the correct data set. To do so, we typed head of MyData and the first 6 rows are displayed. Now, let us jump into the analysis. The first thing we do to start off with analysis is descriptive statistics of the data set. We get this in R by typing summary of MyData. Now we can see the summarized information of each and every variable in the data set. We have the minimum value, the maximum value, and first and third quartile value, the median and the mean value given for each of the variables. Let's see for the bedrooms count variable. We see that the apartments have a minimum of 0 bedrooms, which might correspond to studio apartments, and a maximum of 7 bedrooms. The median value is 3, specifying that apartments with 3 bedrooms are the most common. The first quartile, as we know, is the middle value between the smallest number and the median of the data set. For bedrooms, this value is 3. Similarly, the third quartile is the middle value between the median and the highest value in the data set. For the bedroom count variable, this statistic is equal to 4. The mean is almost 3, again showing that the apartments in this locality generally have 3 bedrooms. The individual summaries can be obtained by using the $sign, as we have already discussed. If we observe the summary data, we will find that material and level don't have the usual statistics like the quartiles, mean or median value given for them. They are instead classified into their types and the number of occurrences of each type. We can see that most houses are brick houses, having the highest count, and aluminum wood houses are the least common. From the level variable, we can see that a majority of the houses are two-storied. There are only 3 ranches and 7 split-level apartments, and the rest are all two-storied. So constructing a two-storied apartment would be a very safe bet in this neighborhood. However, obtaining the summary of my data doesn't give us information of other important statistical terms, like the standard deviation, variance, etc. This statistical information is important to make further decisions and for analysis. Though R has individual statistic functions like the SD, var functions to obtain these values, we will use a library package to obtain all the statistics. R has a package named Basix that can be installed by using the install.packages function and included in the current working session by the library function. We use the stat.desc function to obtain a comprehensive statistical summary of the data. So we type stat.desc of the data frame. That is, my data in this case study. And here we can see statistics like the number of values, number of nulls, number of NA values, the range of values in the variable, the sum of all the values, the standard error of the values from the mean, the confidence interval mean for a 95% confidence level, the variance value, the standard deviation value, and the coefficient of variance. Let us look into the statistical description for a particular variance, say garage count, and understand these factors. The first row, nbr.val, give the number of values, that is, 57. The nbr.null value is 6, which means there are totally 6 records in our data set that have a garage count of 0. Then nbr.na shows a value of 0, which means that there are no not applicable situations. The next row is minimum value, and it displays 0. So that means there are houses with 0 or no garages. The max column shows a value of 2. So their maximum number of garages in an apartment is 2. Next, we can see the range. Range is nothing but the difference between maximum and minimum value. We can say that there are a 0 to 2 garages in the apartments belonging to this locality. Next factor is sum, and the value displayed is 73. So in this locality, there are 73 garages. The next is median, and its value is 1 for garage count. That is, most apartments have 1 garage. We have a mean value of 1.28, however. We cannot take the literal interpretation, since the number of garages must be a whole number. The next factor is standard error of mean. It is usually estimated by dividing the sample estimate of the population's standard deviation by the square root of the sample size. Next factor here is confidence interval mean. When we compute a confidence interval on the mean, we compute the mean of a sample in order to estimate the mean of the population. For our example, the standard error and confidence interval mean do not add much meaning to the interpretations, so we ignore these values. To understand these values, let us analyze the selling price variable of our data set. The selling price of apartments in the locality varies from $13 million to $84 million. The standard error mean here is 1.69 million. The confidence interval mean for a 95% value is twice the standard error. That is 3.4 million. We know that we are working on a sample data set. The mean of the sample data of apartments is around 34 million. What the confidence interval tells us is that we can say with 95% confidence that the mean of the population will vary between 34 plus or minus 1.69 million. That is 32.31 to 35.69 million. Next, we have the variance of the selling price. The variance is quite high, as you can see here, 164.38. The standard deviation is 12.8 million. This logically makes sense as we have our data ranging from studio apartments to partial apartments with 6 bedrooms. And the prices of these apartments will have a large variation. And the last factor we can see is coefficient of variance. This shows the percentage of variation from the mean. For the selling price, it gives a value of 0.37. That is, there is a 37% variation of values around the mean. Let us view the selling price data in a histogram. Type hist of selling price. From the results, we see that there are buckets of 10 to 90 million, increasing by 10 million each. Most of the houses are sold in the $20 to $40 million range, and there are no houses sold in the $60 to $80 million range. There are 2 apartments sold above 80 million. We are interested in knowing what is unique about these apartments. To view just these 2 records, we will subset the data. Type my data of my data dollar selling price greater than 80 and comma. 2 records are displayed. We know that wooden houses generally have a higher selling price. Also, the count of rooms is pretty high for these 2 apartments. The first data has a very high age value and might have sold higher because of its vintage value. Now, let us find the variations in selling price according to their number of rooms, number of bedrooms, etc. As seen in the lesson, we will use the aggregate function for this purpose. We attach the data frame to the session by attach of my data. Now, let us aggregate first by number of bedrooms. Type aggregate of selling price tilde bedrooms count and specify function as mean. We get the corresponding average selling price for each number of bedrooms. We can see a steady increase in selling price as the bedroom count increases. From 1 to 2 bedrooms and 4 to 5 bedrooms, there is a jump in the selling prices. Apartments with 3 or 4 bedrooms have almost the same average selling price. The apartments with 5 bedrooms have the highest selling price, so apartments and people in this locality are willing to pay more for apartments with 5 bedrooms. We should also remember that both apartments that sold highest had 5 bedrooms, and thus the average results might not be the right statistic due to the presence of outliers. Let us do a similar check on the selling price according to the garage count. There is a huge difference between the average selling prices of apartments with no garages and 2 garages. So adding a garage might be beneficial in increasing the selling price. The next thing that we would be doing with the dataset is to see which factor is actually affecting the selling price of the apartments. That is, whether the pricing is affected by the house material, or the number of rooms, or the living space per square feet, etc. So, to find out the variables responsible for pricing, we will do correlation. The correlation will tell us about how much the variables correlate with each other, and also with respect to the pricing factor of the houses. Here, another thing to keep in mind is that in our data set, we even have variables which are categorical. As we already know, correlation can only be performed on numerical values and cannot be performed on the other values. So how do we go about solving the issue with the categorical variables? One way to go about this is to manually select the numerical data. There is an easier option too. That is, we can specify an attribute to the correlation function which states to select only the numeric values. The function Laplace of x comma function f returns a list of same length of x. After applying the function f on each of the data item, we will use this function with the is.numeric function to remove non-numeric values. So, let's type core of my data of unlist of Laplace of my data common is.numeric. So now we can see the correlated value of every numeric variable with every other numeric variable in the dataset apart from the material and level variables. Let's check which of the variables has the highest correlation with the variable selling price. Looking at the selling price column, or row, we see that the local price has the highest correlation value of 0.79. The living space per square feet variable is a very close second, having a correlation of 0.789 with the selling price. So, the selling price is strongly correlated with the local price and the living space of the apartment, as suggested by the correlation of almost 80%. We can see that age in years has a negative correlation with the selling price with a value of minus 0.21. Thought the correlation coefficient is quite low? We can see that an increase in the age for apartments tend to decrease its market value. Performing correlation for all the variables against all the other variables is more advantageous as it compares all the variables and helps us in getting insights which might not be visible by just looking at the data. For example, we can see that garage count has a mild correlation with almost all variables. So the number of garages to be built for an apartment is quite independent of the number of rooms or bedrooms or the living space. However, the presence of a garage tends to have an increase in the selling price, as can be seen from a correlation of 0.4 with the selling price. Now suppose we don't need to correlate entire table. Need to test the correlation between two variables. In such cases, we can just type core.test and mention the two variables whose correlation we want to know. Suppose we want to know how much the number of rooms is related to the price of a house. So to correlate selling price with number of rooms, we type core.test of rooms count, comma, selling price. Here we can see the results to be 0.55. From this value, we can understand that there is about 54% relationship between the number of room counts and selling price. Also, the p-value is very less, which supports the hypothesis that the two variables are related. The next test we will perform on the data is ANOVA, analysis of variance, as we have seen in a collection of statistical models used to analyze the differences between group means and their associated procedures. The calculations of ANOVA can be characterized as computing a number of means and variances, dividing two variances and comparing the ratio to a handbook value to determine statistical significance. Here we shall perform ANOVA on selling price with two categorical variables we have in the data set. Let us first test the means per the level variable and store it in a variable called fit. So we type fit equals to AOV of selling price tilde level data equals my data. Now type fit and we can see the ANOVA result. The first factor we can see is sum of squares. It is the deviations from the sample mean. From the ANOVA result between selling price and level, the sum of squares value is 43, and the residuals is 9,162. The next factor, number of degrees of freedom, is the number of values in the final calculation of a statistic that are free to vary. In this case, degree of freedom of level is 2, and residuals are 54. Next type summary of fit, we get other parameters like the mean squared value, F statistic, and P value. The very low value of F statistic and higher value of P value imply that we cannot reject the null hypothesis. The obtained P value is 0.8, quite high compared to the standard value of 0.05. When we analyze the levels variables, we see that most of the apartments fall in the two-story category. This kind of skewness affects the ANOVA since their number of observations in each group is highly unequal. Let us view this graphically by using the plot function. Type plot of selling price tilde level gives us a box plot of the selling prices for various values of levels. We can see that two-story and ranch apartments have a high variance, whereas split-level prices vary very little. Also, for two-story, there are 2 outliers in the data. A similar ANOVA can be done with material and selling price too. So type fit equals AOV of selling price tilde material, comma, data equals my data, and we can see the ANOVA results for material. We see the sum of squares value for material is 637.88. Residuals value 8,567.61. The degrees of freedom of material is 3, and residuals is 53. Next, we type summary of fit, and we can see the other parameters. Similarly here, even though the F value is comparatively higher, the P value is higher than the standard value, and hence we cannot reject the null hypothesis. We will view a similar plot as earlier by typing plot of selling price tilde material. The apartments constructed with wood have a comparatively lesser variance. There are 2 outliers in this graph as well, and correspond to brick wood and wood categories. Here, we have performed a comprehensive descriptive statistics on the data and some inferential statistics depending on the data we have at hand. It is very important to note that the type of tests and the statistics that we use depend entirely on the business need and the type of data we have. It is common in analytics to be sidelined from the purpose of the research or analysis by applying various tests on the given data. Through this case study, we have provided an example of when to apply which statistic and where to apply different tests of significance to arrive at meaningful insights. Let's look at an experiment to understand the use of t-tests. A researcher studying the effect of a drug on the growth of tumors wishes to find if the drug reduces the growth of tumors. The researcher obtains mice with tumors and divides them into 2 groups. One group of mice was injected with the drug, and the other group was used as the control group. After 1 week, the tumors were weighed again, and the results were noted as follows. The research question is, does the drug reduce the tumor size? In the given table, we can see the tumor size of mice treated with the drug and the tumor size of the mice belonging to the control group. Since these 2 belong to 2 different groups of mice and have no dependencies with each other, we will use independent t-tests. Let's recall the assumptions for independent t-tests. The samples are random. The measured values on a continuous scale. The independent variable is measured on 2 groups or categories. That is, in our case, the experiment and the control group. The observations are independent and follow an almost normal distribution. There is homogeneity of variations. And lastly, there should not be any significant outliers. Since our data adheres to all the above assumptions, we can continue with the significance test. The researcher wants to know if the use of the drug decreases the tumor size. Hence, it corresponds to a one-tailed hypothesis test. Remember that two-sided hypothesis tests will be used when the research question is whether there is a difference in tumor size as the result of the drug. In the video, we will look at how to perform a t-test for this study and if the hypothesis is proved or rejected. Let's start by loading the dataset into R. Step 1. Make sure the working directory in R is set to the directory with the data file, using the getwd and setwd commands. Step 2. Create a data frame, tumor data, and read the file using the read.csv command. The argument to the command is the name of the CSV file with the extension .csv. Step 3. As seen earlier, the head command displays the first 6 rows of the data. Type head of tumor data to display the first 6 rows of the data. Step 4. Before planning the t-test, let us visualize the data using box plots. Type box plot of tumor data to create box plots of the 2 columns. The plots are created and displayed in a new window. Here you can see that the median of tumor size for mice not treated with the drug is higher than the mice treated with the drug. Also, the quartiles or deviations from the median are higher for the control group. Step 5. Next, let us perform the t-test to find whether the drug has an effect on the tumor size. As shown in the previous video, the t-test command is used to perform the t-test. Before performing the test, let us attach the data frame by typing the command attach of tumor data. Now type t.test of treated with drug, comma, not treated with drug, comma, alternative equals L. The alternative equal to L is used to specify that the test is a one-sided test, and we are concerned about the lower tail, that is, if the tumor size is lesser. On hitting enter, the test results are displayed. The t-value is given as minus 2.0643, and the degrees of freedom is 13.651. Using these two values, the p-value is generated as 0.02927. The next columns display the 95% confidence interval, that is, minus infinity to minus 0.009. The sample estimates are displayed below. The mean of x and the mean of y. X and y are used to denote the 2 columns. Here we can see that the mean of tumor size for the experiment group is 0.675, and the mean of tumor size for the control group is 0.742. The null hypothesis for this case study is that there is no difference between the means of the 2 groups. Correspondingly, the alternative hypothesis states that the true difference in means is less than 0. With a significance value alpha of 0.05, we can reject the null hypothesis, since the p-value is less than 0.05. Thus, we can conclude that the drug has an effect of the size on tumor in mice, and the tumor size reduces as an effect of the drug. With this, we complete the concepts of basic analytic techniques. Now, we will look at a business case to illustrate the concepts that we have learned in this lesson. Let's quickly summarize what we have learned in this lesson. We have discussed a basic introduction to R, data exploration using R, data visualizations in R, pie charts, bar plots, box plots, histogram. diagnostic analytics using R, chi-squared test, t-tests, analysis of variance. The quiz section will help you check your understanding of the concepts covered. This includes Lesson 3, the Business Analytics Foundation with R Tools course offered by Simplilearn. Thank you for your attention.
After completing this lesson, you'll be able to explain the various types of graphics available in R, list the possible file formats of graphic outputs, describe the methods to save graphics as files, and describe the procedure to export graphs in RStudio. With its large set of powerful functions, R defines a flexible graphical environment for the visual representation of data. These graphics that help in meaningful data visualization can be viewed on screen, and users can create precisely customized graphical output. The graphics can be saved in various good quality formats, including PDF, PNG, JPEG, WMF, and PS. Typically, graphs are designed on screen, which can then be replotted on, for example, a PDF file. You can also copy and paste in case of a Word or PowerPoint file. Using R, you can produce a variety of graphical images. Basic 3D plots, scatter plots, bar plots, histograms, box plots, and pie charts are 8 standard statistical plots that R can provide. R can also support heat maps, word cloud, kernel density plots, and line charts. Let us look into details of each of these graphics in the subsequent screens. Plotted on vertical or horizontal bars, bar graphs show discrete comparisons among categorical data. The lengths of the bars, each of which represents a category, indicates the frequency, percentage, or proportion of values that fall into the categories. The syntax to create a simple bar chart is barplot x. In the function, x stands for height, which is a matrix or vector. If the height parameter is a vector, the values of the vector give the heights of the sequence of rectangular bars that make up the plot. Let's look at a few examples of how to create vertical and horizontal bar charts. Here, by using an embedded dataset of MT cars, you can plot bar graphs. To create the first bar graph, you pass gear data to the bar plot function. The default setting for bar orientation is vertical. To plot a horizontal graph, you can pass horizontal equals true as the second parameter to the bar plot function. In the next screen, we'll take a quick look at a few arguments to edit simple bar plots. You can add labels, colors, and titles to the bar plot by using specific arguments. For example, legend.text is useful when the height is a matrix. The arguments xlab and ylab provide the labels for the x-axis and y-axis respectively. Call will define the color of each bar. By default, if height is a vector, then gray is used, whereas if height is a matrix, a gamma-corrected gray palette is used. Main sub gives the overall and subtitles for the bar plot. This demo will show the steps to create a bar chart in R. In this demo, you'll learn how to create bar charts. For this data, we will use the MT cars dataset available in R. Simple bar charts can be created using the bar plot function. You can create horizontal bars by specifying horizontal equals true as an argument to the bar plot function. You can also add title, colors, and legends to bar plot by specifying details in an argument. For more options or help document, type the given command in the console. You can create a stacked bar plot if the input is a matrix. The stacked bar will indicate each column on the matrix. The argument beside specifies if you want the bars to be stacked or adjacent to each other. By default, beside is set to false, and if height is a matrix, a stacked bar graph results. If you set beside to true, then you get the columns of height as adjacent bars. You can create a stacked bar plot with colors and legends as shown in the screen. Here in this example on the screen, it's a matrix of VS and gear data from MT cars datasets. Using the same example as in the previous screen, you can create a grouped bar plot. Reiterating, if the height parameter of bar plot function is a matrix and beside is set to true, then the values in each column are juxtaposed rather than stacked. Here, you use the row names function to set the legend, which will set or retrieve the names of rows or columns of a matrix-like object. In this demo, we'll show the steps to create a stacked bar plot and a grouped bar plot in R. In this demo, you'll learn how to create a stacked bar plot and a grouped bar plot. For this data, we'll use the MT cars dataset available in R. For a stacked bar plot and a grouped bar plot, we'll have to create a table like data from the MT cars dataset using the table function. You can create a stacked bar plot using the bar plot function. You can also add title, colors, and legends to bar plot by specifying details in an argument. You can create a grouped bar plot by specifying beside equals true as an argument to the bar plot function. For more options or help document, type the given command in the console. Pie chart is a type of graph in which a circle is divided into sectors, each representing a proportion of the whole. Pie charts are not as popular as dot plots or bar charts in R. You can create pie charts using the function pi x, labels equals. Here, x is a vector of non-negative numerical quantities. The value of x indicates the area of a pie slice. Labels are character strings or expressions that give names to vectors. In the example shown here, you first create the slices vector, which contains numbers 10, 12, 4, 16, and 8. LBLS is the labels vector. Then you pass both these vectors to the pie function as parameters. To set the overall title for the plot, you pass main as a parameter. In this screen, you can see how percentages can be added to the pie chart. In the given example, out of the data vector, you can create the PCT vector and a character vector, LBLS, to add actual labels to the slices. To paste data to the labels vector and add the percentage sign, you use the paste function. Another character vector, call, helps fill in or shade the pie slices. Let's now see how you can create a three-dimensional pie chart. Using the Plottrix package, which has the Pie3D function, you can produce 3D representations of pie charts. There is an explode parameter that enables the pieces to be separated on the chart. However, you first have to install the Plottrix package and reference it using the library function install.packages Plottrix library Plottrix. This demo will show the steps to create a pie chart in R. In this demo, you'll learn how to create pie charts. Pie chart graphics are not available by default. You'll have to install the Plottrix package by using the given command. After installing, you'll have to load the package into R using the given command. For this demo, we'll create a custom dataset using vectors. We can create pie charts using the pie function in the Plottrix package. We can also add a title and labels by specifying the details in an argument. You can create 3D pie charts using the pie 3D function in the Plottrix package. For more options or help document, type the given command in the console. Let's look at another visual representation of data distribution, the histogram. Histograms are a great way to get to know your data. A histogram has an x-axis, a y-axis, and bars of different heights. The bars group ranges of values or continuous categories on the x-axis, and the y-axis shows how frequently the values on the x-axis occur in the data. They display the distribution of a continuous variable and the frequency of scores in each bin on the y-axis by dividing the range of scores into bins on the x-axis. As shown on the screen, the syntax for a histogram is hist in R. For a given set of data values, the generic function hist works out a histogram. If plot equals true, plot.histogram plots the resulting object of class histogram before it's returned. You can create a histogram using the histx function, where x is a vector of values for which you want to plot the histogram. Instead of frequencies, the option frequency equals false plots probability density when you want a histogram of proportion. To control the number of bins, that is bars, use the breaks equals controls option. The break argument helps you control the bin width along with the number of break points you desire. In the example shown on the screen, you can see histograms for dark green colored bins that indicate the miles per gallon or MPG value of the MT cars dataset. A more effective way of visualizing numeric variable distribution, kernel density plots are created using the plot density x function as shown on the screen. Here, x is a density object. You can use the density function to compute the density parameter in plot. In the example shown in this slide, You can create a kernel density graph for the mileage per gallon, or MPG, of MT car's dataset by first calculating its density and then creating the graph. In the second figure, use the polygon function for kernel density of the data for MPG. Vertices are given in X, and colors of the area and the border are given by color equals sky blue and border equals black, respectively. This demo will show the steps to create a histogram and density plot in R. In this demo, you'll learn how to create histograms and a density plot. For this demo, we'll use the MT cars dataset available in R. Histograms can be created using the hist function. You can also specify the number of bins and the color of bin as arguments to the hist function. For the density graph, we'll have to calculate the density of data using the density function and then use the density data to plot the density graph using the plot function. You can color the curve representing density using the polygon function. For more options or help document, type the given commands in the console. Line charts represent a series of data points, called markers, connected by a straight line. This type of graphical visualization is typically used to display data that changes over time. As shown on the screen, the syntax for a line chart is lines, x, y, type equals, where x and y are coordinates of the points. Type indicates the type of plot to be drawn, say L for line and P for points, or B for both. Let's now look at an example of a line chart. In the code shown in this slide, you can create weight and months vectors, and then plot a line and points graph together by calling the plot function. These two vectors are passed as parameters along with main to set the title of the graph as baby weight chart. Also known as whisker diagrams, box plots display the distribution of data that is based on the 5-number summary. Minimum, smallest value in the data set. First quartile, 25th percentile. Median, 50th percentile. Third quartile, 75th percentile. Maximum, largest value in the data set. And data is broken into 4 quartiles in box and whisker plots, and each quartile has the same number of data values. Although these plots do not display the frequency, they show where the middle of the data is, a feature that is really useful if you want to analyze the skewness of your data. The syntax to create a box plot is shown on the screen. Box plot data. A box can be created either for individual variables or for variables by group. As shown on the screen, the syntax is boxplot x data equals, where x is a formula and data equals denotes the data frame providing the data. To make the widths of the box plot proportional to the square roots of the number of observations in the sample, use var_width equals true. With horizontal equals true, you can reverse the orientation of the axis. Default false means the box plots are vertical. In the code shown here, a vector of numbers was created and the summary function called to print the values of the following variables: minimum, first quartile; median, mean third quartile; maximum. Then the box plot function was used to display the box plot for the vector of numbers. This demo will show the steps to create line graphs and a box plot in R. In this demo, you'll learn how to create line graphs and a box plot. For this demo, we'll create custom dataset using vectors. We'll use the plot function to create line graphs. Points in a line graph can be connected by specifying type equals b as an argument in the plot function. We can create box plot using the box plot function. For more options or help document, type the given commands in the console. Heat maps are two-dimensional representations of data in which the values are represented by colors. The two types of heat maps are simple and elaborate heat maps. A simple heat map provides an immediate visual summary of information. An elaborate heat map allows you to understand complex data sets. Rows and columns can be clustered in a heat map, and the result of the hierarchical clustering computation is shown as a dendrogram in the heat map. As shown on the screen, the syntax to create a heat map is heat map data row v equals NA, column v equals NA. Here, row v and column v decide if and how row and column dendrograms should be calculated or reordered. Data refers to the matrix of values that has to be plotted. Let's look at an example that shows you how to create a heat map. In the code shown here, you can create a data frame by reading data from a CSV file and converting it to a data frame before passing it to the heat map function. Besides data, row v and column v as not applicable, color as 256, and scale as columns to plot a heat map graph are passed to the heat map function. This demo will show the steps to create a heat map in R. In this demo, you'll learn how to create a heat map. For this demo, you'll use the custom dataset imported from a CSV file. A heat map can be constructed using the heat map function. You can also specify the color and scale details as arguments to the heat map function. For more options or help document, type the given command in the console. Also known as tag clouds or text clouds, word clouds highlight the most commonly cited words in a text using a quick visualization. Creating a word cloud in R is relatively simple using a text mining package, TM, and word cloud generator package, word cloud. As shown on the screen, to create a word cloud, use the syntax word cloud, words equal data, frequency equals frequency, min.frequency equals 2, etc. You need to install the word cloud package into the R environment using the install.packages, word count, and library word count commands. In the example on this screen, text data is read from a CSV file, and a word count graph is plotted using the word count function. Passwords, frequency, min.frequency as 2, max.words as 100, and random.order as false. The minimum.frequency argument specifies the minimum frequency below which words that have a frequency lower than that value will not be plotted. The maximum number of words to be plotted are determined by the max.words argument. Random.order means that the words will be plotted in a random order. If false, the words are plotted in decreasing frequency. This demo will show the steps to create a word cloud in R. In this demo, you'll learn how to create a word cloud. Word cloud graphics are not available by default. You'll have to install the word cloud package using the given command, and then load the package using the other command. For this demo, we'll use the custom data imported from the CSV file. We can use the word cloud function to create a word cloud. We can also specify the minimum frequency and maximum word as arguments to the word cloud function. For more options and help document, type the given command in the console. Let's now take a look at the various file formats for saving your plots. R supports several graphic formats and runs on different operating systems. Consequently, there are many formats to choose from depending on what you want to do with the graph, how you connect remotely or locally, and what operating system you use. A few of the available formats are as follows. JPEG doesn't resize and can be used anywhere. PDF, easily resizable and is the best choice with PDF latex. PNG, doesn't resize and can be used anywhere. WMF, easily resizable and works on Windows only. Best choice with Word. PostScript, easily resizable and is the best choice with OpenOffice and latex. On the slide, you can see an example to save a graphic output as a file. Regardless of the way you connect or the type of operating system you use, the general method that will work on any computer that has R involves the following steps. Select the file format you want. For example, if you want to save your plot as a JPEG file, use the JPEG driver, which only requires the name of the file that you will use to save the graph. Note that your plot will be stored relative to the current directory, which can be found by typing getwd at the R prompt. Entering your plotting commands next will save those to a file. Then use the dev.off command to close the file. Either you will get a partial plot or nothing in case you fail to enter the dev.off command after you are done with the plotting commands. So if you want to save a JPEG file called myplot.jpg containing a bar graph, you will type the commands as shown on the screen. Recalling the example from the previous screen, you will see that you need to re-enter the commands to save your plot to a file after making a plot to the screen. However, in R, there is another command, dev.copy, which will copy the contents of the graph window to a file without the hassle of re-entering the commands. In this approach, produce the graph as you usually do, and then call dev.copy along with the arguments that are appropriate to the driver. For example, to create a myplot.jpg file from a graph shown by R, type the commands shown on the screen. Until you call dev.auth, the plot isn't actually written to the file. This demo will show the steps to save graphics to a file in R. In this demo, you'll learn how to save graphics to a file. You can save a graphic as a JPEG file using the JPEG function. You'll also have to use the dev.auth function to return the control to the console back again. For more options and help document, type the given command in the console. In this screen, let's see how you can export graphs in RStudio. Follow these steps to export graphs in RStudio, a powerful interface for R. In the graphics panel of RStudio, click the Plots tab. Click the Explore menu and select the Save as Image menu item. The Save Image window is displayed. Select the image format and directory to save the file. Click the Save button. Follow these steps to export graphs as PDFs in RStudio. In the Graphics panel of RStudio, click the Export menu and select the Save as PDF menu item. Select the directory to save the file. Click the Save button. This demo will show the steps to save graphics using RStudio. In this demo, you'll learn how to save graphics using RStudio. You can save a graphic from RStudio by clicking the Export menu and selecting Save as Image. Select the directory to save the file, and then click Save. Let's summarize the topics covered in this lesson. R includes powerful packages of graphics that help in data visualization: bar chart, pie chart, histogram, kernel density plot, line chart, box plot, heat map, word cloud. You can save the outputs of graphics in various file formats, such as PDF, PNG, and JPEG. You can export graphs in RStudio by using the graphics panel.
Python and R are top programming languages that are in demand in data science community. Both have their own pros and cons. Therefore, it is vital that you understand the crucial differences between the two programming languages and decide which one is the best fit for you. After watching this video, you will understand which language is better for you in terms of different parameters. Before unwrapping today's topic, I request you to subscribe to our channel and press the bell icon to never miss any updates from Simplilearn. And also get notified every time you get a similar video. Now let us look at what are we covering today. We are covering Introduction to R and Python, Parameters in R and Python, Best Tools and Libraries offered by Python and R, and Conclusion to the topic. Introduction to R and Python. Let me ask few queries regarding Python and R. R language is superficially related to Python, C, C++, Java. Please leave your answer in the comment section below and stay tuned to get the answer. And another question is, which one of the following is a Python file extension? .p, .python, .py and .pyt. Please leave your answer in the comment section below. Coming to Introduction to Python and R. R is a statistical programming language and environment that integrates statistical computing and graphics. R is powerful and stable software. Python can also be called as a general-purpose programming language for data analysis and scientific computing. Python can be considered as the best player in machine learning. Python is an expressive language with many built-in functions. Both are open source software and platform independent. And they are platform neutral and also compatible with all major operating systems including Unix, Windows and Mac. Next, we will be covering different parameters. We will be covering learning preferability, mathematical fundamentals, speed of both the languages, visualization and graphics, data handling capacity, demand, community and customer support, employment possibility in both the languages. Let us cover it one by one. First one is learning preferability or ease of learning. Python is renowned for its ease of use. Python's notebooks offer excellent tools for sharing and documentation despite the fact that there are currently no GUIs for them. Programmers find R as difficult language as a beginner. This implies that the programmers must devote a significant amount of time to learn and comprehending R coding. Coming to mathematical fundamentals required. Coming to Python, understanding descriptive analysis is very important. In layman's terms, descriptive statistics often refers to the process of explaining using certain representative techniques such as charts, tables, Excel files, etc. Python statistics is a built-in library for descriptive statistics. If your data sets are not too big or if you can't rely on importing other libraries, you can use Python. On the other hand, R requires basic statistics. From basic statistics, what I mean is mean, mode and median are the terms used most frequently in basic statistics. It is referred to as measures of central tendency. Probability statistics plays an important role in handling various types of probability distribution. It includes binomial and normal distribution. Next parameter is speed. Python is an interpreted language with dynamic typing. Python always executes slowly because the code is executed line by line. Compared to MATLAB and Python, R language is significantly slower. R packages are substantially slower than those for other languages. Now that we have covered speed, coming to data visualization and data collection in Python. When selecting data analysis tools, visualization are crucial and Python has some incredible visualization tools. In Python, to large and varied scatter plots using regression lines, we can use ggplot2 and ggplot tools. Compared to raw values, visualized data is easier to comprehend. Therefore, R has many packages that offers sophisticated graphic features. In R, we can use tools like matplotlib, Seaborn, etc. Data handling capability in both Python and R. The new releases in Python have resolved the issue with the Python packages for data analysis. R is useful for analysis because of the abundance of packages, accessibility of the test, and benefit of employing formulas. However, simple data analysis can also be done using it, the need to install many packages. Crucial part of parameter, that is tools and libraries in Python and R. As a Python developer, one needs to be well versed in the best libraries because Python has a lot of libraries that have many different uses. Libraries like TensorFlow, Scikit-learn, NumPy plays an important role in solving many Python-related problems. Libraries perform a wide variety of tasks in R that are very beneficial for data science operations. Example for that is dplyr, bioconductor, etc. Community and customer support index offered by Python and R. Compared to R, Python has a larger community. For assistance, we can contact www.python.org. For any queries regarding Python and help, you can you can visit support.realpython.com. For any help and queries, R offers you with RStudio community. R provides assistance through its official website. For queries and community related issues, we can contact www.r-project.org. Next is job opportunities in Python and R. A recent survey from Indeed.com predicts that at least 55,000 Python jobs in the USA with exponential pay rates are available. Big tech companies like Google, Amazon, Twitter, Facebook requires Python developer to handle massive amount of data. Position provided for a Python developer is software engineer, data analyst, data scientist, and many more. Career in R is an excellent job opportunity for you as a beginner. Big tech companies like Google, Twitter, Facebook are using R. Position provided by companies as a R developer is data scientist, data analyst, data visualization analyst, etc. Moving on, let us wrap up an important topic, which language to be used between R and Python. There is no right or wrong way to study both Python or R. Both are in demand skills that will enable you to complete almost any data analytics work you come across. It ultimately depends on your background, interest, and career objectives that which one is better for you. But compared to R, Python is easy to learn. Let's compare its strengths and weaknesses. It is used to handle large amount of data. Python performs non-statistical functions and it is best suitable for programming. However, Python is better when it comes to coding. Whereas R is used in data visualization graphics, R is a widespread language in the statistical community. It is used to accomplish many mathematical tasks. So before concluding the topic, let me answer the query that I have asked regarding R and Python. Do you guys remember the question? The query was, R language is superficially related to which language? So the answer for the question is C language. Next question was, which one of the following is a Python file extension? It was an easy question. Answer for that question is .py. Simplilearn offers you with the best courses for both Python and R. Certification offered by Simplilearn regarding R is Data Science with R certification course. It is a skill-up course that contains 64 hours of applied training, 10 real-life industry projects, dedicated mentoring session from industry experts, and finally, lifetime access to self-paced learning. I will provide the link for this course in the description below. Data Scientist for Python. It is a best course for a beginner. It includes 5 courses in collaboration with IBM at an affordable price. Courses includes Python for Data Science. After that, we will be covering Applied Data Science with Python, Machine Learning, as well as Tableau Learning, and Data Science Capstone. And finally, receive a master's certificate with individual certification for each course. I will provide the link for this course in the description below.
In the world of data science, Python stands out for its ease of use and powerful data analysis capabilities. Reflecting on the 2023 Stack Overflow Developer Survey, Python's popularity is unmatched, especially among data analysts and scientists. Consider the success story of Anna, a data analyst whose expertise in Python's pandas and NumPy libraries led to the development of a predictive model that significantly influenced her startup strategy. This example highlights Python's practical application in extracting meaningful insights from data, a skill highly valued in the industry. As you gear up for a Python data analyst interview, it's crucial to demonstrate not only your technical mastery of Python, but also your ability to apply its functionalities to real-world problems. This guide focuses on essential interview questions and answers, drawing from real-life applications and challenges to prepare you for what lies ahead. Through understanding practical use cases like Anna's, you will gain insights into the impactful role Python plays in data-driven decision-making. So, we will start with the first question, that is, what is Python and why is it preferred for data analysis? So, Python is like a versatile tool that's not only easy to use but also powerful enough to tackle big projects. It's a programming language, which means it's a way for us to write instructions that a computer can understand and execute. What makes Python special is how it combines simplicity and power. It's as if the tools in this section of the supermarket are designed to fit comfortably in your hand and work exactly as you expect, making your job easier. So here I will be giving you an overview of the answers you can provide to the interviewer in the interview. So now you might wonder, why do people working with data love shopping in the Python section so much? So let's consider some points for that would be easy to learn. So Python's simplicity means you can learn how to use it quickly even if you are never programmed before. It's like learning to cook using recipes that requires only a few ingredients. Then comes versatile toolset. Python offers a variety of tools known as libraries, specifically designed for data analysis. Imagine having a Swiss Army knife but for data. These tools can help you clean, sort, analyze and visualize data all in one place. Then we have community support. So there's a huge community of people who use Python for data analysis. So if you ever get stuck or need advice, there's a good chance someone has been in your shoes and can help. It's like having a group of friends who are always there to lend a hand. And then comes integration and automation. So Python makes it easy to automate repetitive tasks and integrate your data analysis work into larger projects. This can save you a ton of time and effort, allowing you to focus on the fun parts of your project. Then comes the in-demand skill. Because so many businesses rely on data to make decisions, knowing how to analyze data with Python is a valuable skill that can open doors to exciting job opportunities. So this is how you can answer the interview about why is Python preferred for data analysis. So moving to the next question, that is, explain the difference between a list, tuple and dictionary in Python. So I will give you an overview. You could use this or just mold it to your language and provide the answer to the interviewer. So when discussing the structures, that is list, tuple and dictionary in Python, it's like looking at different ways to organize information. Each serves a unique purpose. Lists are akin to an adjustable shelving unit. You can add, remove or change the items on freely. It's ordered, meaning you can refer to each shelf by its position. For example, you could see an example here, that is my underscore list, and we have put pencil, notebook and eraser in the list. So it allows you to manipulate the contents as needed. Now coming to the tuples, so tuples resemble a fixed display case. Once you have arranged your items inside, their order and presence are set. You cannot change them. This immutability is useful for ensuring that certain data remains constant. So you could see the example. So I have changed the example. So you could see here that my tuple has pencil, notebook and eraser. So it signifies data that you don't intend to alter. Now coming to dictionaries, so they are like a flying cabinet or the filling cabinet with labeled folders. Each folder or key holds specific items values, making it easy to locate what you need quickly without concern for the order in which you added them. So you could see an example, that is my underscore dictionary that has pen and it is pointing out for the blue, then book that is pointing out to mathematics. That provides a way to access items directly by their label or key. Now moving to the next item or the next question, that is, how do you handle missing values in a pandas data frame? So when working with data in Python using pandas, it's common to encounter missing values. Think of missing values like puzzle pieces that are lost. To complete the puzzle or analyze your data, you need to decide what to do with these missing pieces. So strategies to handle missing values. The first one will be remove. So if the missing value is like a lost puzzle piece that isn't crucial, you can simply remove that row or column. This is straightforward but can lead to losing valuable information if not done cautiously. For example, you could just use df.drop_na. So this is how you could use it. Now coming to the next option, that is fill in. So if you think of the missing piece as something you can guess or approximate, you can fill in the missing value with a guess. This could be the average of the ordered pieces, the most frequently appearing piece, or a placeholder like 0. For example, you could use df.fillNA and you could pass the value inside it. So the choice between removing and filling in depends on your specific dataset and what you are trying to achieve. If maintaining the integrity of your data without the missing pieces is crucial, filling in might be the best option. If the presence of incomplete data could skew your results, removing those entries might be safer. So this is how you could tackle this. Now moving to the next question, that is, what are lambda functions in Python and where would you use them? So imagine you are in the kitchen about to make a quick snack. You could pull out a big food processor for a small job, but sometimes it's easier to use a simple knife. In Python, lambda functions are like that handy knife, a quick one and a one-time tool for small tasks. So let's understand the lambda function. Lambda functions are small anonymous functions defined within the lambda keyword. They can have any number of arguments but only one expression. Perfect for when you need a simple function for a short period. You could see the syntax, that is basic form, lambda arguments, expression. Now we'll see its examples of use. Number one is sorting. Imagine you have a list of names with their ages and you want to sort them by age. Lambda function makes this simple. So you could see the code here, that is sorted, and under we have passed list, key equal to lambda x of 1. So this is how you could do that. Then comes the quick calculation. So you need to quickly apply a mathematical operation like squaring a number without writing a full function. So you could have a example here. So this is how you could have a square of a number. So when to use lambda functions? So now we'll see when to use lambda functions. Number one is short one-time use. That is ideal for when you need a function once or in a limited scope. And number two would be simplicity, when the operation is simple enough to be expressed in a single line. And then comes the inline operations, that is useful for inline operations that requires a function. So let's move to the next question, that is question number 5. And the question is, demonstrate how to use list comprehension to simplify code that generates a list of square for all even numbers from 0 to 10. So imagine you are tasked with creating a beautiful garden path using square stepping stones. However, you only want to use stones that fit certain criteria, such as being even numbered in size. In Python, list comprehensions offer a concise way to create this path with just the stones you need. So let's understand list comprehension. So list comprehension provides a succinct way to create list. They combine a loop, conditionals, and the list operation into one line. It's like selecting specific items based on criteria to create a new collection. And now we'll see the basic syntax for that. That is, in the form, you will write the expression for item and then the iterable and if condition. So let's see an example. So we'll create a list of square for all even numbers from 0 to 10. So first we'll do this with the traditional approach. And here we have an array, and then we'll use the for loop and then if statement, and then we'll append if the number is even, we will square it. Now coming to the list comprehension approach, so you could see the expression here. So first is the condition, then the for loop, and then the if conditional. So this is how the list comprehension works. So now we will discuss about the key points of list comprehension. So the number one is efficiency. So list comprehensions make your code more readable and efficient. Number 2 is simplification. They simplify multiple lines of code into a single readable line. And then comes versatility, useful for filtering items or applying operations to elements. And now coming to the next question, that is sixth one. Explain the concept of deep and shallow copy in Python. So imagine you have a magical notebook. Whatever you write in it also appears in a linked notebook. If you have a shallow copy of the notebook, changes to the content like adding a new page in one will show up in the another. However, if you change something on a page already existing in both notebooks, only the original notebook's page is affected. A deep copy is like having two completely independent magical notebooks. Whatever you do in one notebook, whether adding new page or changing existing ones, doesn't affect the other notebook at all. So let's understand shallow copy and deep copy. So shallow copy creates a new object but does not create copies of nested objects found within. Instead, it just copies the reference to these objects. So changes to nested objects in the original or the copy will reflect in the other. So you could see an example for that, that is import copy, and then we have the original list, and the shallow copied list is equal to copy.copy of the original list. Now moving to the deep copy. So it creates a new object and recursively copies all objects found within the original object, nested objects included. So changes in the original or the copy do not affect each other at all. So let's see the example, that is deep underscore copied underscore list equal to copy.deep copy, and inside we have passed original list. Now we'll discuss about the key points. So shallow copy, that is good for saving memory when creating copies of large objects where nested objects aren't modified. And about the deep copy, so it used when you need a fully independent copy of an object, including all nested objects. So this was about deep copy and shallow copy. Now moving to the next question, that is what is PEP8 and why is it important in Python programming? Imagine you are playing a game where everyone agrees on certain rules to make the game more fun and fair for everyone. In the world of Python programming, PEP8 serves a similar purpose, but for writing code. PEP8 stands for Python Enhancement Proposal 8, and it's essentially a set of rules and guidelines for formatting Python code. So let's understand PEP8. So PEP8 is like the rule book for Python code style. It covers recommendations on how to format your code, such as how to name variables, how to indent your code, and other best practices. Think of it as the etiquette for Python programming. Ensure that everyone writes code in a consistent and readable way. And let's discuss why PEP8 matters. So the number one reason is readability. Just like a well-organized book is easier to read, code that follows PEP8 is easier for humans to understand and read. It's about making your code not just functional but also presentable and approachable. Then comes collaboration. When everyone uses the same style guide, it's much easier to work on projects together. This consistency removes confusion and helps prevent errors that arise from misinterpreting the code. And then comes maintenance. So code that's easy to read and understand is also easier to maintain and update. If your code follows PEP8, anyone including future you can quickly understand and modify it as needed. So following PEP8 is like keeping your code's desk clean and organized. It makes your Python programs more enjoyable and easier for you and others to read and work on, just as playing a game is more fun when everyone knows and follows the rule. Coding in Python is more effective and enjoyable when everyone adheres to PEP8. So this was about PEP8. Now moving to the next question, that is describe how to perform a merge operation between two pandas data frames. So imagine you are at a dinner party and you have two guest lists. One list has the names of guests and their favorite dishes. The other list has names with their preferred drink choices. To plan your dinner menu, you need to combine these lists into one. So you think each guest food and drink preferences side by side. In Python's pandas library, this combining of lists or tables is called a merge operation. So let's understand merge in pandas. So first we'll see pandas. So it's a powerful library in Python for data analysis and manipulation. And merge operation is like joining two tables based on a common column, like guest names in our example, so that you can see all the information in one place. So let's see the steps to perform a merge. Number one step is identify the common key, that is find the column common to both data frames such as guest name. Then choose the type of merge. Decide how you want to combine your list. Do you want to include all guests, only those present on both lists, or some other criteria? And then use the merge function. Apply pandas merge function to bring your data frames together based on your criteria. You could see the example here. That is, first we will identify the common key and then we'll choose the type of merge as you could see like outer join, inner join, or both the criterias. And then we have used the merge option. So this is done, that is to perform a merge operation between two pandas data frame. Now moving to the next question, that is ninth question, and that is, can you explain what NumPy is and how it is better than a regular list in Python? So imagine you have a toolbox. In this toolbox you have a regular hammer, that is Python's list, and a power hammer, that is NumPy. Both can drive nails into a board, that is perform numerical operations, but the power hammer does it faster and with less effort, especially when you have a load of nails, large dataset. NumPy stands for Numerical Python, and it's a library especially designed for numerical operations. It introduces an object called an ND array, that is n-dimensional array, that is more efficient than Python's regular list for a few reasons. Now we'll see those reasons. Number one is performance. So NumPy arrays are stored at one continuous place in memory, allowing faster access in comparison to list. So this means operations on NumPy arrays can be done much quicker than on list. Then comes functionality. NumPy comes with a vast library of mathematical functions that can be performed on arrays, making it incredibly powerful for scientific computing. And then comes memory efficiency. A NumPy array is more memory efficient than a list, allowing you to work with larger dataset. So this is why NumPy is better than a regular list in Python. Now moving to the next question, that is, how do you improve the performance of a slow running Python script? So imagine you are in a race with a backpack full of tools you think you might need. As you run, you realize the backpack is slowing you down. So to speed up, you would streamline your backpack, carrying only what's essential and being organized for quick access. Optimizing a Python script follows a similar principle. So here's how. Number one is profile before optimizing. First, find out where the heavy items are. Use profiling tools to identify the slow parts of your script. It's like checking your backpack to see what's making it too heavy. Then you can use efficient data structures. Some data structures are faster than others for certain tasks. It's like choosing a lightweight, compact multi-tool over carrying separate tools for each job. You could leverage NumPy for numerical tasks. If your script does a lot of mathematical calculations using NumPy, as we discussed earlier, you can significantly speed things up, similar to swapping out a manual tool for a power tool. And then you could avoid global variables. Accessing global variables is slower than accessing local ones. It's akin to having the tools you frequently use in an easily accessible pocket rather than in the bottom of a backpack. And you could use built-in functions and libraries. Python's built-in functions and standard libraries are optimized for speed. Using them instead of custom solutions can be like using a well-paved road instead of hacking your way through the jungle. And then you could use limit of loops. So loops, essentially nested ones, can slow down a script. Where possible, use Python's list comprehensions or NumPy's vectorized operations. It's like choosing a path that goes directly to your destination instead of wandering around. So by focusing on these strategies, you could significantly improve the speed of your Python script, making your coding race more of a sprint than a marathon. Now moving to the 11th question, that is, what is the purpose of the group by function in pandas, and provide an example of its use. So let's say you have a big box of crayons sorted by color. You want to count how many crayons you have in each color. In Python's pandas library, the group by function helps you do exactly that with your data. So the group by function groups data in a data frame based on a certain criteria, like how you might group crayons by color. So once grouped, you can apply functions to each group independently, such as counting them, summing up values, or calculating averages. So here how it works. Number one is group. So the first group by that separates the data into groups based on your chosen criteria. It's like sorting your crayons into groups of the same color. Now coming to the apply. So next it applies a function to each group. This could be calculating the average, sum, count, etc. If we are sticking with the crayon analogy, this is like counting how many crayons you have in each color group. And then comes combine. Finally, it combines the results into a new data frame. You end up with a summary of your original data organized by the grouping criteria. So it's like having a neat list that tells the count of each color of crayons. So now moving to the next question, that would be 12th. So how can you create visualizations using Matplotlib or Seaborn? Provide an example. So imagine you have just taken a beautiful hike and you want to share the experience with your friends. You could describe every detail in words, or you could show them a photo that captures the essence of the adventure. In data analysis, Matplotlib and camera and filters for data, allowing you to create visual representations that capture the insights from your datasets. So talking about Matplotlib, that is the camera. So Matplotlib is a plotting library in Python that allows you to create a wide range of static, animated, and interactive visualizations. Think of it as your camera for data visualization, giving you the tools to create basic graphs like line charts, bar charts, and scatter plots. And then comes the seaborne. But before that, you could see the example here, that is import matplotlib as PLT. Then we have X and Y, and they have the numbers there, and then you could plot the graph there. And then comes the seaborne, the filters. So seaborne is built on top of matplotlib and provides a high-level interface for drawing attractive and informative statistical graphics. So seaborne is like adding filters to your photos, making your visualization more aesthetically pleasing and easier to interpret with less code. And you could see the example here, that is import seaborne as SNS, and then you could set the theme and the line plot. Now coming to the next one, that is 13th question. So now guys, let's understand overfitting. So overfitting occurs when a machine learning model learns the details and noise in the training data to the extent that is performs poorly on new data. It's like memorizing the answers to a test rather than understanding the subject. And now we'll see how to prevent overfitting. So number one is use more data. So having more data can help the model learn better and generalize well. It's like learning more about types of fruit to improve your overall understanding. Then comes simplify the model. Sometimes using a simpler model can prevent overfitting. This is akin to focusing on the basic characteristics of fruit, like color and shape, rather than memorizing every spot on the apple's skin. And then comes cross-validation. This technique involves rotating the dataset through training and validation phases. It's like practicing with different sets of fruit every time to ensure you really understand them, not just memorize them. And then comes regularization. So this technique adds a penalty on the more complex features of the model. Think of it as discouraging the model from paying too much attention to the less common characteristics of the fruit. And then comes early stopping. During training, if you notice that your model's performance on a validation set starts to worsen, stop the training. It's like realizing you are starting to focus too much on the details that don't matter and stopping your studying to refocus. And in conclusion, overfitting is like studying too hard on the specifics and missing the big picture. By using strategies like gathering more data, simplifying your model, and practicing with cross-validation, you can help your machine learning model to learn better and be more adaptable. Just like a well-rounded student who understands the essence of the subject, not just the details. Now moving to the next question, that is 14th. Describe a situation where you had to clean a large dataset, and what steps did you take? So imagine you have just been given a giant old attic full of various objects to organize and clean up. Some items are valuable and need to be kept, some are duplicates, and others are just plain junk. Cleaning a large dataset in Python is somewhat similar. You are aiming to tidy up the data so that it's useful for analysis. So we'll see the steps for cleaning a large dataset, that is remove duplicate data. That is just like removing duplicate items in the attic that you don't need more than one of. In datasets, duplicates can skew your analysis. So for that, we'll use the action as we have seen the number one step, that is remove duplicate data, and we'll see the action, that is we'll use dataframe.drop underscore duplicates in pandas to remove them. And then we can use another method, that is handle missing values. So imagine finding boxes that are supposed to contain items, but some are empty. You decide whether to fill them, label them as empty, or remove them altogether. For that, we could do the action, that is options include dataframe.fillNA to fill missing values, or dataframe.dropNA to remove rows or columns with missing values. And then we have correct data types. Sometimes objects are stored in the wrong boxes. Similarly, a numeric column might be incorrectly formatted as text. So for that, we'll use dataframe.asType to correct data types. And then we have standardized the data, ensuring everything is organized and labeled consistently, like making sure all book titles follow the same format. For this action, we will apply functions to clean and standardize text, numbers, and dates. And we have remove or correct outliers. If you find something completely out of place, like a snowboard in a box of summer clothes, you decide if it's an error or if it should be stored somewhere else. So the action we can use is use statistical methods to detect outliers and decide whether to keep, adjust, or remove them. And in conclusion, cleaning a large dataset involves removing unnecessary parts like duplicates and outliers, filling in gaps, that is missing values, and organizing, correcting data types, and standardizing. It's about making sure the data is accurate, consistent, and ready for analysis, just as organizing and cleaning the attic that makes it easier to find and use what you need. Now moving to the next question, that is 15th. How do you split a dataset into training and testing sets using scikit-learn? Imagine you are preparing for a magic show. Before performing in front of a live audience, you practice your tricks with a friend to get feedback. Similarly, when you are working with machine learning models, you need to practice or train your model on a portion of your data and then test it on another portion to see how well it performs. So this process helps ensure your model can perform magic with new, unseen data, not just the data it learned from. So we'll see using scikit-learn to split data. So scikit-learn is like your magic kit for machine learning in Python. It has a tool called train_test_split that makes dividing your data into training and testing sets a breeze. So we'll see the steps to split your dataset. Number one is prepare your data. Gather your dataset. It's like getting all your magic props ready for the show. Then import the tool. Bring the train_test_split function into your project. And then we have split the data. Decide what portion of your data you want to train on and what portion to test on. The common split is 80% for training and 20% for testing. And you could see the code here. And here X represents your features, that is the information you use to make predictions, and Y presents your target, what you are trying to predict. And then we have text size equal to 0.2 that tells the function to reserve 20% of the data for testing. And in conclusion, splitting your data set into training and testing sets is a crucial step in the machine learning process. It's like rehearsing your magic tricks before the big show, ensuring your model is well prepared to amaze with its prediction on the new data. Using scikit-learn's train_test_split, this process is simple and straightforward, allowing you to focus on perfecting your model's performance. That is 16. Explain the difference between supervised and unsupervised learning with examples. So imagine you are learning to paint. In supervised learning, you have an instructor who gives you a picture to paint and guides you, telling you when you are putting or getting it right and where you need to improve. So this is like having labeled data in machine learning, where you know the correct answers or labels for your training data, and you are trying to predict those answers for new data. So in supervised learning, however, it's like you are given brushes and paints, but no pictures to replicate and no instructions. You are free to explore and create patterns or structures on your own. In machine learning, this means working with data without predefined labels, and the goal is to identify patterns or groupings within the data, such as clustering similar customers together. So key points are here are supervised learning. You have labeled data, and the goal is to learn a mapping from inputs to outputs. And examples include regression and classification problems. So now moving to the key points for unsupervised learning. That is, you work with unlabeled data, and the goal is to discover underlying patterns or structures. The examples include clustering and dimensionality reduction. Now moving to the next question, that is 17th question. And what are the main steps in a machine learning project? So embarking on a machine learning project is like planning a journey. You need a map to guide you through different terrains and landmarks. And here's how this journey typically unfolds. Number one is define the problem. So first figure out your destination. What do you want to achieve with your machine learning model? And this step is about understanding the problem you are trying to resolve. For second point, gather and prepare data. So next, pack your backpack. You need data for your journey, collect data for your problem, and then clean and pre-process it to make it useful for training a model. Then choose a model. Now choose a model of transportation. Different models like decision trees, neural network, etc. have their strength and are suited for different types of problems. And then train the model. Time to hit the road. Training a model is like teaching it the rules of the road. You will feed it the data you prepared earlier, allowing it to learn from it. And then evaluate the model. Check your map and compass. How well is your model performing? Use separate testing data to evaluate its accuracy and make sure it's learning correctly. And then fine-tune the model. So find the best route based on the evaluation, adjust your model's parameters or approach to improve its performance, and then deploy the model. You have reached your destination. Once your model is trained and fine-tuned, you can deploy it to start making predictions or insights on new data. And then we can monitor and update. That is, keep an eye on the road conditions. Over time, your model might need adjustment or retraining as it encounters new data or as the underlying data patterns change. So this is about the main steps in a machine learning project. Now moving to the next question, that is, how do you evaluate the performance model? So imagine you have baked a batch of cookies for the first time. To know if they are good, you need people to taste them and give you feedback. Similarly, after you have trained a machine learning model, you need to evaluate its performance to see how well it's doing for its job, like predicting outcomes or classifying data. So the steps would be, number one is accuracy. So this is like asking, out of all the cookies, how many were just right? In classification problems, accuracy measures how often the model's predictions are correct. And then confusion matrix. Imagine a chart showing the types of feedback: too sweet, just right, too bland. A confusion matrix helps you understand not just the successes, but also where and how the predictions went wrong. And then comes precision and recall. Precision asks of all the cookies we labeled as just right, how many truly are just right? Recall asks of all the cookies that are actually just right, how many did we correctly identify? It's about being correct when you say it's right and finding all the right ones. And then comes F1 score. Sometimes you want a single number to balance precision and recall, especially if you have unsure which one is more important. The F1 score is like an overall grade for your cookies that considers both taste and appeal. And then comes ROC curve and AUC. Imagine plotting a graph showcasing your cookie making attempts, balancing how adventurous you are with flavors against the mistakes you make. So the ROC curve plots true positive rates against false positive rates, and the AUC, area under the curve, gives you a single measure of how good your model is across different thresholds. Now moving to the next question, that is provide an example of using SQL in conjunction with Python for data analysis. So imagine you are a detective trying to solve a mystery. You have a huge room full of file cabinets, your database with information of various cases. Now you need a smart, efficient way to find exactly what you are looking for without rummaging through every file by hand. Here's where Python and SQL join forces to help you out. So the Python and SQL, the detective duo. So SQL is like your search tool for query of the database directly, pinpointing the exact information you need, such as details of a specific case. And you know Python, that is like your assistant detective that helps you to analyze the information, draw insights, and present them in a way that's easy to understand. So now we'll see a simple scenario. You are interested in finding out the number of cases solved each month to see when your team was the most effective. So use SQL to retrieve data. So you write a SQL query to extract the number of cases solved by month from your database. So you could see how we have written here, that is select month and count as case solved, and from case files where status is equal to solved, group by month. So now we will analyze and visualize with Python. So you use Python to connect to the database, run your SQL query, and then use libraries like pandas for analysis and matplotlib or seaborn for visualization. So you could see here that we have imported pandas and matplotlib, and then we have connected the SQL here, and then we have run the SQL query and load into a data frame, and then we have plotted the graph. So you could see the example how we have used SQL in conjunction with Python for data analysis. Now moving to the next question, that is 20th question, and how do you handle error handling in Python? And can you explain the use of try, except, and finally blocks? So let's dive in. Imagine you are walking through a forest on a path you think you know well. Suddenly you find a tree that has fallen across your path, and you need a plan to deal with the unexpected obstacle. In Python situation, this is like running into an error in your code. So the try, except, and finally blocks help you navigate these unexpected errors gracefully. So the try block, this is where you walk along your planned path. You place the code that you think might cause an error inside the try block. It's like saying, I will try to go this way, but there might be a tree in my path. And then we are coming to the except block. So if you encounter a fallen tree, an error, the except block is your alternate route. This block catches the error and lets you handle it, preventing the program from crashing. You can specify different types of trees to look out for and different detours. So you could see the example here, that is try walking the path, except, oh no, a tree, take a detour. So you take a detour from here. And then we have the finally block. Whether you encountered a tree or not, the finally block is like reaching the end of your walk and taking a moment to reflect. So this block runs no matter what. Even if there was an error, it's often used for cleanup actions like closing a file or releasing resources. So you could see the code here, that is finally relax at the end. So here's the conclusion, guys. So we have covered 20 questions for you. So if you like this video, please like, share and subscribe. If you have any doubts, comment them in the comment section below.
And with that, we have come to the end of our full course. Now, if you have any doubts or questions, you can ask them in the comment section below. Our team of experts will reply to you as soon as possible. Thank you and keep learning with Simplilearn.